Hello there, and welcome to the Cosmographer. Every place on tonight's countdown can be seen, photographed, and measured, and not one of them can ever be visited. We will rank 20 of them, from number 20 down to number 1, by how firmly the universe has closed each door. Among them is a world whose single year lasts 11,400 of hours, a calendar that has not completed even half a year since human history began. Among them is a giant planet 640 light-years away, where astronomers can tell you, from Earth, that molten iron is raining on the night side this evening. Among them are the towers in the most famous photograph in astronomy, which every telescope on Earth sees only as they were when writing was being invented. And the place at number 1 is not a single destination at all. It is most of everything that exists, and its door, measured only in recent decades, has already quietly closed. Get comfortable and settle in. If falling asleep to the universe's locked doors sounds like your kind of night, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this countdown, you will know exactly how much of the universe can still be reached, and why that answer keeps shrinking. Now, let's begin at number 20. Number 20, the point in space where you started this video. Tonight's list is a map of 20 real places that no human being, and in most cases no human machine, will ever visit. That is a strong claim, and this video intends to earn it slowly, place by place, over 3 hours. Some of these destinations are sealed by heat and pressure, some by distance, and some by the shape of space and time itself. All of them share one strange property. We can see them. We can measure them, photograph them, and in several cases describe their weather. We simply cannot go. The list is ranked, from number 20 down to number 1, by how firmly each door is shut. It begins with doors of physics, moves outward through doors of distance, and ends with doors built into the geometry of the universe. And the number 1 entry, waiting at the end of the countdown, is not a single destination at all. It is a measured amount of everything that exists, and the measurement is not small. The first unreachable place on this list is closer than the room you are lying in. It is the point in space you occupied when this video began. That sounds like a riddle, so let us walk through it carefully. The Earth is moving. It circles the Sun at about 30 kilometers every second, which is roughly 107,000 kilometers per hour. A passenger jet crosses the Atlantic in about 7 hours. The Earth covers that same distance in under 4 minutes, and it never stops to refuel. So in the few minutes since you pressed play, the planet has carried you thousands of kilometers from where you started, and there is no vehicle on Earth that could take you back to that spot, because the spot is behind us in a direction no road runs. The motion does not stop there. The Sun itself is in orbit around the center of our galaxy, carrying the Earth and everything else with it at about 230 kilometers per second. One full circuit of the galaxy takes somewhere between 225 and 250 million years. The last time the Sun occupied this side of the Milky Way, the first dinosaurs were only beginning to appear. Every fossil in every museum formed somewhere else in the galaxy, at a place the Earth has long since left. And there is a third layer. Our whole neighborhood of galaxies, called the local group, is drifting through the universe at roughly 600 kilometers per second, measured against the afterglow of the Big Bang, the most universal reference frame nature provides. Add the layers together, and the arithmetic becomes almost comical. In the time it takes to hear a single sentence of this narration, you have been carried hundreds of kilometers from the point where the sentence began. By the end of this video, the place where you started it will lie millions of kilometers behind you. Hold on to that phrase, a few hundred kilometers behind you, because it will return at the very end of this list, wearing a much larger meaning. Here is the part that makes this a genuine entry, rather than a party trick. You might imagine planting a flag at that abandoned point, some marker hanging in space that says, "Here is where the video began." Physics does not permit it. Space has no fixed grid. There is no cosmic surveyor's stake, no absolute address, nothing to anchor a position to once you have left it. Isaac Newton imagined space as a fixed stage on which the universe performs. Albert Einstein retired the stage. In relativity, positions exist only relative to things, and the things are all moving. The point where you began this video is not hiding somewhere, waiting to be found. It exists only in the past, and the past is not a destination any engine can reach. There is something quietly wonderful in this. Every person who has ever lived has been an interstellar traveler, covering hundreds of kilometers of space with every breath, without feeling any of it. Motion through the universe is the one journey nobody can refuse, and home, in the strict sense, is a place none of us has ever stood in twice. It is fair to ask how we can even know these speeds, given that none of them can be felt. The answer for the last and largest of them is one of the loveliest measurements in cosmology. The afterglow of the Big Bang, the cosmic microwave background, fills the sky in every direction, and it should look almost perfectly uniform. It does not quite. In the 1970s, and definitively with the COBE satellite, astronomers measured that the glow is very slightly warmer in one direction of the sky and very slightly cooler in the exact opposite direction. That pattern is a Doppler shift, the signature of our own motion. We are plowing through the oldest light in the universe, compressing it faintly ahead of us and stretching it faintly behind us, and the size of the effect hands us our speed, around 600 kilometers per second, toward the constellations Leo and Crater. The universe, it turns out, comes with a speedometer built into the sky, and every observer who ever measures it will find their own private reading. The sun's galactic voyage adds its own texture to the story. Our star does not simply circle the Milky Way on a flat racetrack. It bobs slowly up and down through the galactic disk as it goes, rising above the plane of the galaxy and sinking back through it every 30 million years or so, like a carousel horse completing its gentle cycles. It drifts through spiral arms and out of them, through star-forming regions and quiet stretches. The sky your ancestors saw 10,000 generations ago was measurably different, and the stars of every constellation you know are themselves in motion, so that the Big Dipper of 100,000 years from now will be a shape with no name. Nothing in the night sky is holding still. The stillness is a trick of the shortness of human lives. And this is why the entry is not a technicality but a genuine door, permanently closed. To return to the point where you started this video, you would need a way to stand still while the Earth, the Sun, the galaxy, and the local universe all moved on without you, and physics offers no such thing as standing still. There is no cosmic anchor to drop, no absolute harbor. Every atom in your body has been on an uninterrupted journey since it formed, through spans of space that dwarf every distance in the rest of this countdown, and not 1 meter of that journey can ever be walked back. The universe does not offer return tickets, even to the space behind your own head. It only offers the road ahead. But the nearest unreachable place with a permanent address sits at the center of our own daylight, and it has been broadcasting its inaccessibility into your window every morning of your life. Number 19. The core of the Sun. The core of the Sun is about 150 million kilometers away, which is 8 light minutes, close enough that its consequences land on your skin every clear afternoon. It occupies roughly the innermost quarter of the Sun's radius. The temperature there is about 15.7 million Kelvin. The density is about 150 times that of water, which makes the material in the core around 13 times denser than lead, and yet it is not solid. It is plasma, packed by the weight of an entire star pressing inward. The numbers describing its activity deserve a moment of quiet attention. Every second, the core fuses about 600 million tons of hydrogen into helium. In that same second, roughly 4 million tons of matter cease to be matter at all and become pure energy, following the most famous equation in physics. 4 million tons per second sounds destructive, and it is, but the Sun is so large that it has been running this furnace for 4.6 billion years and has burned through less than half of its usable fuel. The engine of every harvest, every rainstorm, and every photosynthesizing leaf on Earth is a room we can never enter. And we have tried to get close. The Parker Solar Probe, launched in 2018, became the fastest object humanity has ever built. On December 24, 2024, it passed just 6.1 million kilometers above the Sun's visible surface, moving at 692,000 kilometers per hour, fast enough to cross the United States in about 25 seconds. To survive even that grazing pass, it hid behind a heat shield facing temperatures near 1,000 degrees Celsius. That is the record. The core lies another 700,000 kilometers below the surface the probe skimmed, beneath an ocean of plasma at millions of degrees, under pressures no material in any laboratory can withstand. The nearest sealed room in the universe is sealed by the building around it. Yet we know the Sun's core in remarkable detail, because the core sends out messengers, and the two kinds of messenger tell a story that borders on poetry. The first messenger is light itself. A packet of energy born in core fusion does not fly out of the Sun. It random walks, absorbed and re-emitted by the crowded plasma over and over, gaining a fraction of a millimeter of progress at a time. The best estimates say the journey from core to surface takes on the order of 100,000 years, and some calculations stretch it toward 170,000. Then, once free of the surface, that same light crosses the gulf to Earth in 8 minutes. Think about what that means for the sunlight on your face. It is fossil light. It was manufactured in the core before the last ice age ended, before any city existed, and it finished its journey this morning. The light can make the trip. We cannot. Keep that sentence too, because it is the organizing law of this entire list. The second messenger is the neutrino, a ghostly particle that barely interacts with matter at all. Neutrinos made in the core do not random walk. They stream straight through the entire body of the Sun in about 2 seconds and reach Earth about 8.5 minutes after they were made. Trillions of them are passing through your body as you listen to this sentence, doing nothing, touching nothing. Far beneath a mountain in Italy, a detector called Borexino spent years catching a precious few of them, and from those catches physicists confirmed, reaction by reaction, exactly which fusion chains are burning at the heart of our star. We have also learned to read the Sun's interior the way geologists read earthquakes. The Sun's surface rings with slow vibrations, and the science of helioseismology uses those oscillations to map the layers beneath, sounding a place that light itself needs 100 millennia to escape. So the core of the Sun is that rare kind of unreachable place, one we understand intimately and can never confirm with our own instruments on site. Every probe melts 100,000 kilometers too early. Every image shows only the glowing skin. The heart of the nearest star will spend its entire 10 billion-year life unvisited, while its light keeps arriving, 100,000 years stale and 8 minutes fresh, on every world it warms. The architecture between the core and the daylight is worth a moment, because it explains the 100,000-year traffic jam. Around the core lies the radiative zone, a region 300,000 kilometers thick, where energy moves only as light, hopping from particle to particle through plasma packed too densely for any bulk motion. This is where the great delay happens, the region where a photon's path becomes a drunkard's walk of trillions of absorptions and re-emissions. Above it, the physics changes personality entirely. In the outer third of the Sun, the plasma thins enough to boil, and energy rides upward in rising columns of hot gas, a layer of convection whose churning tops we can actually watch. The surface of the Sun, seen up close, is a pavement of bright granules, each one a convection cell about the size of Texas, rising, cooling, and sinking on a timescale of minutes. Between the two zones lies a thin boundary layer called the tachocline, where the Sun's inner clockwork grinds against its outer boil, and where many solar physicists believe the star's magnetic field is born. The Sun is not a simple ball of fire. It is a layered machine, and we have reverse-engineered nearly all of it from the outside of a sealed case. The neutrinos, meanwhile, earned their trustworthiness the hard way. Beginning in the late 1960s, a physicist named Raymond Davis ran a detector far down a South Dakota gold mine, a tank of 600 tons of cleaning fluid, and counted the solar neutrinos passing through it. He caught them, a handful of atoms worth per month, but only about a third as many as theory predicted, and for 30 years this shortfall, the solar neutrino problem, hung over physics. Either we misunderstood the Sun's core, or we misunderstood neutrinos themselves. The answer, established around the turn of the millennium by detectors in Japan and Canada, was the second option, and it was Nobel-winning news twice over. Neutrinos oscillate. On the flight from the Sun's core to Earth, they shift among three types, and Davis's experiment could see only one type. The Sun had been running exactly as calculated all along. Consider what that episode actually was. A sealed room 150 million kilometers away disagreed with a tank of cleaning fluid under a mountain, and the argument was settled without anyone visiting either the room or, in any ordinary sense, the mountain. That is how astronomy interrogates the unreachable. There is also a long goodbye written into this entry. The core's story does not end with the Sun as we know it. In about 5 billion years, the hydrogen at the center will run out, and the core, compressing and igniting the shell around it, will drive the Sun to swell into a red giant that swallows Mercury and Venus and possibly Earth. When the outer layers finally drift away, what remains will be the core itself, laid bare at last as a white dwarf, an Earth-sized ember of crystallizing carbon and oxygen that will cool for tens of billions of years. The most sealed room in the solar system will end its story as the only part of the Sun left standing, finally visible, finally naked to space, and by then there may be no one in the neighborhood left to look. The light's long escape is also a demotion, and the details are worth savoring. Energy leaves the core as gamma rays, the most energetic form of light there is, and if that radiation reached us unaltered, the Sun would be lethal rather than life-giving. The 100,000-year traffic jam is what tames it. With every absorption and re-emission in the crowded plasma, the energy is subdivided and softened, one gamma ray gradually broken into thousands of photons of gentler light, so that what finally leaves the surface is mostly the mild visible glow our eyes evolved to harvest. The delay is not a quirk. It is the difference between sunshine and sterilization, 100 millennia of bureaucracy that converts a bomb into a lamp. And the lamp is not constant. Models of stellar evolution show the core densifying and warming as it converts hydrogen to helium, brightening the Sun by about 10% every billion years. The sealed room at the center is slowly turning up the thermostat of every world it owns, on a schedule written in its own inaccessible interior, and the Earth's distant future, oceans and all, is being decided in a chamber nothing can visit. There is one more measure of the core's isolation worth holding up against the rest of this list. Distance is not what seals it. A mere 150 million kilometers separates your bedroom from the Sun, a gap our probes cross routinely, a gap light crosses in 8 minutes. What seals the core is a column of star, 700,000 kilometers of plasma, standing between the surface and the center, the most impassable 700,000 kilometers in the solar system. Compare the two journeys. Voyager 1 has traveled 25,000 times farther than the depth of the Sun and remains in perfect working order. No conceivable machine survives even 1% of the way down into the star next door. On this list of unreachable places, the second entry from the top of the countdown establishes the theme in its purest form. Reachability was never really about distance. It is about what stands in the way. And the next sealed interior on our list is not a star at all. It is a planet, the largest one we have, and unlike the Sun's core, we have actually touched its outer threshold. Once. For less than an hour. Number 18. The interior of Jupiter. On December 7, 1995, a small machine built by human hands arrived at the doorstep of this entry. The Galileo spacecraft, after a 6-year cruise from Earth, released a cone-shaped atmospheric probe about the size of a large barbecue grill, aimed at the cloud tops of Jupiter. The probe hit the atmosphere at 47.4 kilometers per second, which remains the fastest atmospheric entry any human object has ever performed. In the first 2 minutes, it decelerated at about 230 times the force of Earth's gravity. The gas ahead of its heat shield was compressed into a glowing sheath, roughly twice as hot as the surface of the Sun. Half of the shield's mass burned away. And the probe survived, opened its parachute, and began to fall. Let us fall with it for a moment. The parachute snaps open, and the violence of entry gives way to a slow, swaying descent through haze the color of sand and rust. There is no floor below, and there never will be. The clouds part into canyons of deeper cloud. Ammonia crystals give way to darker decks, and lightning flickers somewhere far off to one side, illuminating cloudscapes the size of continents. The pressure climbs past Earth's sea level, then past double, then past 10 times. The temperature, freezing at first, warms steadily, then uncomfortably. The little probe keeps talking the whole way down, streaming numbers upward to the orbiter passing overhead, wind speeds, pressures, chemical abundances, the first and only direct readings from inside a giant planet. 57 minutes into the descent, about 160 kilometers below the cloud tops, with the pressure at roughly 23 times Earth's atmosphere and the temperature past 150 degrees Celsius, the transmitters fail, one after the other. The probe falls on in silence. It is still falling, in a sense. Its materials melted, then vaporized, and its atoms are now part of Jupiter, dissolved into the planet it came to study. It is worth pausing on the people behind that hour. Engineers spent a decade designing and building a machine they knew would live for less than 60 minutes at its destination, and they spent that design effort making sure it would spend every one of those minutes talking. Nothing human has ever gone deeper into any world beyond Earth. The probe's final transmission, crackling up from beneath the clouds, remains the only voice ever to speak from inside a giant planet. Devotion, in planetary science, is sometimes measured in minutes of data. And here is the humbling part. Those 160 kilometers were barely a scratch. Jupiter is about 70,000 kilometers deep from cloud top to center. The probe's entire heroic descent covered roughly 1/500th of the way down. Below where it died, the atmosphere thickens without any surface, and hydrogen, squeezed harder and harder, stops behaving like a gas at all. Thousands of kilometers down, it becomes a supercritical fluid, neither gas nor liquid. Deeper still, at pressures millions of times Earth's atmosphere, hydrogen undergoes one of the strangest transformations in nature. Its electrons are squeezed free, and it becomes a liquid metal. Jupiter contains an ocean of liquid metallic hydrogen, tens of thousands of kilometers deep, a shining sea of metal that no eye will ever see, whose slow churning generates a magnetic field about 20,000 times stronger than Earth's, the largest structure of any kind in the solar system, apart from the Sun's own influence. What sits at the very center was a genuine surprise. When the Juno spacecraft arrived at Jupiter on July 4, 2016, it began mapping the planet's gravity with exquisite precision, reading the interior by the way Jupiter's mass tugged the spacecraft off course by fractions of a millimeter per second. The old textbook picture showed a compact ball of rock and ice at the center, a core you could point to. Juno's data revealed something else. Jupiter's core appears to be dilute or fuzzy, with heavy elements smeared outward through nearly half the planet's radius, blended into the metallic hydrogen like sugar stirred into tea. Perhaps a colossal impact early in Jupiter's history stirred the core into the envelope. Perhaps giant planets are simply born this way. The conditions at the center, pressures around 50 million atmospheres and temperatures near 20,000 Kelvin, cannot be reproduced or fully modeled, and no hull, existing or imaginable, survives the trip down. The deepest place in our planetary neighborhood is permanently off the map, and it is only the second entry from the end of our list. The probe's final hour was nearly lost twice before it began, which makes the hour itself more remarkable. Galileo's main antenna, an umbrella of gold mesh that was to carry the mission's data home in a torrent, jammed partway open on the way to Jupiter and never unfurled, forcing engineers to route the entire mission, probe descent included, through a small backup antenna at a trickle of the planned rate, rescued only by heroic reprogramming and data compression. And the probe's atmospheric entry, when it finally came, turned out to have threaded a needle nobody had aimed at. It happened to strike an unusually clear, dry patch of Jupiter's atmosphere, a so-called hot spot, one of the least cloudy places on the planet, which skewed some of its readings about water and weather. Even our single hour inside a giant planet came with an asterisk about luck. Science later balanced the ledger. When the comet Shoemaker-Levy 9 slammed into Jupiter in July 1994, 17 months before the probe's descent, the scars it tore open gave astronomers a violent, unplanned excavation of the cloud deck, nature's own experiment to compare against the probe's gentle soundings. The metallic hydrogen ocean deserves one more beat of attention because it represents matter in a state Earth has barely touched. Laboratories have spent decades trying to squeeze hydrogen hard enough to force it metallic, using diamond anvils that concentrate pressure to millions of atmospheres, and the claims of success at the very edge of those experiments remain debated, milligram samples held for instance. Jupiter maintains that same state casually, by the planetful, and has for 4.5 billion years. Its metallic sea conducts electricity so well that the planet's rotation churns it into a dynamo, generating the largest magnetic structure in the solar system, a magnetosphere that would appear larger than the full moon in our sky if our eyes could see it, and whose radiation belts are fierce enough that spacecraft near Jupiter must be armored like bank vaults. The unreachable interior does not keep to itself. It reaches out and shapes the space for millions of kilometers around it. Juno's later years added one more layer of intimacy to a place no one will ever confirm by hand. Skimming low over the cloud tops every 53 days, the spacecraft mapped a concentrated knot of magnetism near the equator that scientists nicknamed the Great Blue Spot, watched cyclones the size of continents arrange themselves into geometric rings around both poles, and found that Jupiter's famous winds are not skin-deep weather, but rivers of motion, extending thousands of kilometers down before the interior forces them into lockstep. Every measurement sharpens the same picture, a world with weather on top, metal in the middle, and mystery at the center, and every measurement arrives the same way, from outside, at a respectful distance, from a machine that knows better than to descend. It is worth descending the ladder once, in numbers, to feel how quickly Jupiter closes its door. At the cloud tops, conditions are almost polite, pressures below Earth's and temperatures around -145 degrees Celsius. 160 kilometers down sits the Galileo probe's grave, at a mere 23 of Earth's atmospheres. 1,000 kilometers down, the pressure has climbed toward levels found in Earth's ocean trenches, and the temperature passes the boiling point of water. A few thousand kilometers farther, hydrogen thickens into a supercritical fluid, and the concept of falling begins to fail, because there is no longer a distinct atmosphere to fall through, only an ocean that becomes gradually denser in every direction. Around 80 or 90% of the way out from the center, by radius, the metallic transition begins, and pressures reach millions of atmospheres. At the center, models suggest perhaps 40 to 70 million atmospheres and 20,000 Kelvin, hotter than the surface of the Sun, in permanent darkness. Every rung of that ladder is a fact we possess, and a threshold no machine will cross. The planet publishes its interior in gravity and magnetism, and forbids the site inspection. One comparison places the entry in the countdown's larger pattern. Jupiter contains more than twice the mass of every other planet, moon, asteroid, and comet in the solar system combined, and by volume, it could hold roughly 1,300 Earths. Yet all of that immensity is, in travel terms, nothing. The distance from Earth to Jupiter is a few years' flight, a gap we have crossed with 9 spacecraft. The unreachable part is not the crossing, but the last few thousand kilometers of arrival, the same lesson the Sun's core just taught. The solar system's 2 largest objects sit in our own neighborhood with their doors politely, permanently shut, and the rest of this countdown will only move the locked doors farther away. From a place that crushes its visitors, the countdown now moves to a place that simply outlasts them, a small red world that will not come near again for 11,000 years. Number 17. Sedna at Aphelion. On November 14, 2003, 3 astronomers, Mike Brown, Chad Trujillo, and David Rabinowitz, found a faint point of red light creeping across the sky far beyond Pluto. They named it Sedna, after the Inuit goddess of the sea who lives at the bottom of the frozen ocean, because no name in astronomy had ever suited an object better. Sedna is a world about 1,000 kilometers across, reddish, icy, and profoundly alone, and its orbit is the reason it belongs on this list. At its closest approach to the Sun, Sedna reaches about 76 astronomical units, 76 times the distance from the Earth to the Sun. That closest approach is farther out than every planet, more than twice as far as Neptune. And that is Sedna on its warmest day. At the far end of its orbit, Sedna swings out to an estimated 937 astronomical units, which is about 140 billion kilometers, more than 5 light days from the Sun. A single Sedna year, one full lap of this enormous ellipse, takes roughly 11,400 Earth years. Numbers that size need anchoring. When Sedna last passed through its far point, anatomically modern humans had not yet built a single city. The entire history of writing, agriculture, pyramids, empires, printing presses, and spaceflight fits comfortably inside one loop of Sedna's orbit, with millennia to spare. When Sedna next reaches its far point, everything now standing on Earth will be archaeology, and probably forgotten archaeology. Right now, as it happens, Sedna is inbound. It is approaching its once-in-11 millennia closest pass, which arrives around 2075 or 2076. This is the single friendly window our entire technological civilization will ever get. Mission designers have published concept studies showing that a probe launched in the coming decades, using gravity assists or advanced propulsion, could reach Sedna near that closest approach. Whether any agency funds such a mission remains open. But notice what even success would mean. We would be visiting Sedna at its nearest, most convenient, least characteristic moment, the brief, warm afternoon of an 11,000-year winter. Sedna at Aphelion, Sedna at its far point, the place where this world actually spends most of its existence, is beyond any serious proposal. 937 astronomical units is more than 5 times farther than Voyager 1 has traveled in nearly half a century of flight. A probe dispatched there with any realistic propulsion would need a century or more of travel, and it would arrive at coordinates Sedna itself abandoned generations earlier, because the place and the moment cannot be caught together. You cannot chase a world through an orbit longer than the whole of human history. Stand there anyway, just for a moment, in imagination. The ice underfoot is among the reddest surfaces in the solar system, organic compounds cooked dark by eons of radiation at a temperature near -240 degrees Celsius. Above, the sky is permanently, perfectly black. The sun is still the brightest thing in it, but it has shrunk to a piercing star, bright enough to cast faint shadows, far too weak to warm anything. Noon on Sedna at Aphelion is colder than any night anywhere on Earth. The Milky Way arches overhead, unmoving, and nothing in the sky appears to change, because at this distance, even the sun's gravity has slowed Sedna's motion to a crawl of about 1 kilometer per second, strolling pace for a celestial body. A year here is not a rhythm of seasons. It is a geological era with a sunrise at one end. The discovery itself was a lesson in patience. Sedna announced itself in the survey images by doing almost nothing. Objects in the asteroid belt crawl visibly from frame to frame, and even Kuiper belt objects show a steady drift, but this point of light barely moved between exposures, and its sluggishness was the giveaway. In our sky, slowness is farness. At the moment of its discovery, Sedna was about 90 astronomical units out, which made it the most distant object ever observed in the solar system at that time, and the astonishing part was that it was near its closest approach. It was almost home by its standards, and it was still 3 times farther than Neptune. Mike Brown later wrote that Sedna might be the most scientifically valuable object in the solar system, precisely because its orbit is a fossil, an unaltered record of whatever violence or encounter shaped the sun's earliest neighborhood, if only we could read it properly. Sedna is also no longer entirely alone, and its small family sharpens its mystery. In 2014, astronomers announced 2012 VP113, a second body with a similarly detached orbit that never comes near the planets. A third, with the Hawaiian name Leleakuhonua, followed, its far point estimated to reach past 2,000 astronomical units. The family is now called the Sednoids, and they pose the problem as a group. Every one of them travels an orbit that no existing planet can explain, as if all of them were witnesses to the same forgotten event, each carrying the same unreadable testimony. Counting how few we have found, and how briefly such objects are visible even near their closest approaches, statistical estimates suggest the darkness between Sedna and the Oort cloud may hold thousands of similar worlds, an entire hidden population living on orbits that outlast civilizations. The solar system may keep most of its residents in a district no map yet shows. There is a final, quietly haunting piece of arithmetic in Sedna's calendar. Its orbital period is about 11,400 years, and the entirety of recorded human history is roughly 5,000 years old. This means that in the whole span of the human story, Sedna has not yet completed even half of a single year. The world that watched over the first cities as a nameless point of light has, by its own reckoning, experienced only a season since. If our species is still here, still curious, and still keeping records when Sedna next returns to its far point, we will have become something with a continuous memory of over 11 millennia, a civilization that plans in Sedna years. Its orbit is less a fact of astronomy than a dare aimed at our permanence. One practical footnote belongs here, because it sharpens the entry's edge. Even the optimistic mission studies for Sedna's 2076 perihelion make sobering reading. Concept papers have examined solar sails skimming close past the Sun for a boost, nuclear electric propulsion, and Jupiter gravity assists, and the better designs still require flight times of 20 to 30 years, launched within a fairly narrow window in the coming decades, merely to fly past the world at its nearest. A mission to orbit Sedna, rather than sweep by it at tens of kilometers per second with cameras running, lies beyond every published concept. So the realistic best case for all of human history's engagement with this world is a single brief flyby near one perihelion, a few days of close data purchased with a generation of flight, after which Sedna swings outbound into its 11,000-year night and the file closes. Whatever that flyby fails to ask, no one now alive, and no one for 110 centuries afterward, gets to ask again. Few deadlines in science are enforced by celestial mechanics with quite such indifference. And Sedna carries a mystery in its pocket. Nothing in the present solar system can explain its orbit. No planet reaches far enough to have lifted its closest approach to 76 astronomical units. Something else did this, long ago. A passing star in the Sun's birth cluster, perhaps. Capture from another star's family, perhaps. Or shepherding by a large planet that has never been found, which brings us, conveniently, to the next entry. Sedna, at least, has been found, named, and scheduled. The next place on this list is still hiding, and we cannot reach it for the simplest reason of all. Nobody knows where it is. Number 16, Planet 9, wherever it is. Every other place on this list has coordinates. This one has only a case file. In January 2016, two astronomers at Caltech, Konstantin Batygin and Mike Brown, published a careful argument that our solar system contains a ninth major planet that nobody has ever seen. The evidence was indirect but pointed. The handful of known objects in Sedna's distant family, the bodies that never come near the planets, showed orbits that appeared to cluster together in space, tilted and aligned, as if something large were quietly herding them. The simplest explanation the mathematics allowed was a planet of roughly 5 to 10 Earth masses, orbiting somewhere between 400 and 800 astronomical units from the Sun, taking 10 to 20,000 years to complete a single year of its own. Sit with that possibility for a moment. A world perhaps 4 times the diameter of Earth, a proper planet, larger than anything in the solar system apart from the 4 giants, may be circling our own Sun right now, and we have not found it. This is not a failure of effort. At 600 astronomical units, sunlight is more than 100,000 times weaker than at Earth. A planet there reflects almost nothing. It would be one dim, slow-moving point among billions of stars, and surveys have been sifting those billions for years without a confirmed catch. The hunt has now entered its decisive phase. In the mountains of Chile, the Vera Rubin Observatory has come online, carrying the largest digital camera ever constructed, 3.2 billion pixels in a single instrument. In early 2026, during its commissioning runs, the observatory began issuing automated alerts for anything in the sky that moved or changed, and in one February night alone, it issued more than 800,000 of them. Its 10-year survey of the entire southern sky is widely described by planetary scientists as the direct test. If Planet 9 exists at the brighter end of the predictions, Rubin should catch it moving within a few years. If the survey finds nothing, the hypothesis will be in genuine trouble. Honesty requires reporting that the evidence has wobbled in both directions. A distant body nicknamed Ammonite, discovered with the Subaru telescope, turned out to follow an orbit that does not fit the predicted clustering, and its existence weakens the original alignment argument. Some researchers maintain the clustering was never real, only an artifact of where our telescopes happen to look. And one published speculation proposes something stranger than a planet, suggesting the herding mass could be a primordial black hole left over from the Big Bang, an object with several Earth masses compressed into the size of a grapefruit, which no telescope would ever see directly. The status label on this entry, in the honest tradition of this channel, reads contested and being tested in real time. But suppose the happy outcome. Suppose Rubin finds it, and some night within the decade, a newspaper prints the first orbit of Planet 9. The discovery would immediately create the most frustrating destination in the solar system. At 400 to 800 astronomical units, Planet 9 would sit 3 to 6 times farther than Voyager 1 has traveled since 1977. New Horizons, the fastest probe ever sent toward the outer solar system, would need on the order of 150 years to cross 600 astronomical units, and it had the advantage of knowing where Pluto would be. A dedicated mission with next-generation propulsion might cut the trip to several decades, which is still a career longer than any mission team. A full-sized planet, orbiting our own star, would enter the catalogue as a world our grandchildren's grandchildren might photograph up close, at best. There is rich precedent behind this entry, because astronomy has predicted unseen planets before, and both possible endings of the story have already happened once. The triumphant ending belongs to Neptune. In the 1840s, Uranus kept wandering off its calculated course, and the French mathematician Urbain Le Verrier worked backward from the misbehavior to compute the position of an unseen world that must be tugging it. He mailed the prediction to the Berlin Observatory, and on the very first night of searching, in September 1846, astronomers found Neptune within 1 degree of the predicted spot. A planet was discovered with ink before glass. The humbling ending belongs to Vulcan. The same Le Verrier, applying the same logic to a wobble in Mercury's orbit, predicted a planet inside Mercury's orbit, and for decades respectable observers reported sightings of it. Vulcan does not exist. Mercury's wobble was real, but its explanation was not a planet. It was Einstein, whose general relativity accounted for the discrepancy exactly. Planet 9 will eventually join one of these two lineages. Either the outer solar system's misbehavior betrays a real world, as Uranus's did, or it betrays a gap in our understanding, as Mercury's did, and both outcomes would be historic. It is worth picturing what the object of the hunt would actually be like, if the optimistic ending holds. The leading models suggest a world resembling a small ice giant, a cousin of Uranus and Neptune, perhaps twice to 4 times Earth's diameter, wrapped in hydrogen and helium over ice and rock. At 600 astronomical units, its noon would be a dim twilight, the sun delivering less than 100,000th of the light Earth enjoys, a star bright enough to read by, and nothing more. Surface temperatures would hover within about 40 degrees of absolute zero. Its year, 10 to 20,000 of ours, would mean that in the planet's own accounting, the whole of human civilization has lasted less than half of one of its orbits. And it would be, by an enormous margin, the most valuable unexplored world in the solar system, a pristine giant formed in the sun's youth and exiled to the dark, holding a complete chemical archive of the era that built the Earth. The search itself explains why such a world could hide so long. A planet at that distance moves against the background stars so slowly that a survey might photograph it dozens of times without noticing that it moved at all, and its faintness puts it below the threshold of most all-sky surveys of past decades. Infrared searches, hunting its internal warmth rather than reflected sunlight, have combed the old IRAS and Akari satellite archives, and one pair of candidate detections announced in 2025 was quickly doubted by the hypothesis's own authors, Brown among them, as inconsistent with the orbital dynamics. That is the honest texture of a live search, candidates raised and retired, evidence weighed in public, and a definitive answer, for once in astronomy, plausibly scheduled within a decade rather than a lifetime. The alternatives deserve their own airing, because each one is almost as interesting as the planet. If the clustering of the distant orbits is real but the planet is not there, something else did the herding. One family of models proposes that the Sun stole Sedna and its kin from a passing star in its birth cluster 4.5 billion years ago, orbits inherited rather than sculpted. Another suggests a planet that once existed and was ejected entirely, leaving its fingerprints on the small bodies and then departing into interstellar space, in which case the sculptor of our outer solar system is now a rogue world wandering the galaxy, unreachable in a way that would make even this list blush. And the primordial black hole proposal, however exotic, is at least testable in principle, since such an object would occasionally betray itself by bending the light of background stars. Every version of the story ends with the same moral. The outer solar system remembers an event we were not present for, and the memory is stored in orbits we can read but not yet decode. There is also a scenario in which this entry resolves as a lesson about evidence itself. If the Rubin Observatory's decade of watching turns up hundreds of new distant objects and their orbits show no clustering at all, then Planet 9 will dissolve the way the planet Vulcan dissolved, not disproven by a single observation, but starved by better statistics, a pattern that was never a pattern, an artifact of small numbers and pointed telescopes. Astronomers on both sides have said plainly that this is how science should settle it, with a survey too complete to argue with. Either a world is found and this list loses an entry to the reachable column in a few generations at enormous cost, or a world is unfound and the entry migrates to the catalogue of humanity's instructive mistakes. Both endings are worth staying tuned for, and one of them is scheduled for this decade. For now, it remains the purest entry on this list, a place that may be unreachable twice over, once by distance, and once by the simple, maddening fact that nobody yet knows where to point. Whether or not a ninth planet waits out in that darkness, the darkness itself has a boundary, an enormous shell of ice that wraps the entire solar system, and it is the next stop on our way down. Number 15. The Oort cloud. In 1950, the Dutch astronomer Jan Oort asked a deceptively simple question. Where do comets come from? The great long-period comets that sweep through the inner solar system arrive on orbits thousands of years long, falling in from every direction equally, as if the solar system were enclosed by a spherical reservoir of ice. Oort worked out that the reservoir must be real. It has carried his name ever since. The Oort cloud is the true edge of the solar system, a shell of icy bodies beginning somewhere around 2,000 astronomical units from the Sun and extending, by most estimates, to as much as 100,000 astronomical units. That outer figure deserves translation. 100,000 astronomical units is about 1.5 light-years, a third of the way to the nearest star. The Sun's family does not end at Neptune. It ends nearly halfway to the neighbors. The population of this shell is estimated in the trillions, icy bodies a kilometer across and larger, the leftover construction material of the planets, scattered outward 4.5 billion years ago and preserved ever since at temperatures a few degrees above absolute zero. Their combined mass is modest, perhaps a few times the Earth, spread through a volume so enormous that the average distance between neighboring bodies is measured in tens of millions of kilometers. The Oort cloud is a crowd by census and a desert by experience. And here is the strange epistemic status of this place. No telescope has ever imaged the Oort cloud. Not once, not partially. At those distances, a comet nucleus is billions of times too faint for any instrument we have built or designed. The cloud is known entirely by inference, from the orbits of the comets it occasionally drops into our sky. When a new great comet appears, astronomers trace its path backward and find the far end resting 1,000 times farther than Pluto. Each such comet is a courier from a place we have never seen, carrying pristine ice from the solar system's construction era, postmarked from an address no camera has ever photographed. Now for the arithmetic of reaching it, which is where this entry earns its rank. Voyager 1, launched in 1977, is the fastest outbound object of the classic era, traveling about 17 kilometers per second. After nearly 50 years of continuous flight, it has covered about 168 astronomical units. The inner edge of the Oort cloud lies at 2000. At its current speed, Voyager 1 will arrive at that inner edge in roughly 300 years. It will then need about 30,000 more years to pass through the cloud and out the far side. 30,000 years to cross the suburbs of our own solar system. And Voyager will make that crossing as a dead ship. Its plutonium power source is fading now, and before 2030, its last instrument will fall silent. The same is true of every human artifact currently leaving the solar system, both Voyagers, both Pioneers, and New Horizons. All 5 will coast into the Oort cloud as inert monuments, antennas cold, computers dark, unable to look at the one region of space they alone, of all human works, will ever visit. The first human objects to arrive anywhere beyond the planets will arrive without the ability to say so. There is something almost ceremonial in that image. 5 silent machines drifting for 300 centuries through a cathedral of ice that their builders never saw. The cloud has a future, and it is not entirely quiet. Roughly every 100,000 years, some passing star swings near enough to rattle the shell and shake a rain of comets loose toward the inner worlds. Astronomers have already identified the next such visitor. A small orange star called Gliese 710 is falling toward us now, and in about 1.3 million years it will pass directly through the Oort cloud's outer regions, close enough to scatter comets by the thousand. The solar system's border will be breached, on schedule, by a foreign star, long before any envoy of ours reaches the border from inside. The man who deduced this place deserves a portrait, because his method is the method of this whole entry. Jan Oort was one of the 20th century's great astronomers, the first to demonstrate by measurement that the Milky Way rotates, a pioneer of radio astronomy who helped map the galaxy's spiral arms from a war-battered Netherlands, a man who spent his career extracting enormous conclusions from faint clues. In 1950, he gathered the orbits of the few well-measured long-period comets and noticed that their far points piled up at a particular enormous distance, tens of thousands of astronomical units out, and that they fell inward from every direction rather than from any preferred plane. From that thin file of evidence, he deduced a spherical shell of trillions of unseen bodies wrapping the entire solar system. 3/4 of a century later, every new long-period comet still files its flight plan in agreement with him. It remains one of the largest structures ever discovered by pure inference, a country mapped entirely from its emigrants. The cloud also has an internal geography, and even its nearer province is beyond us. Astronomers distinguish the outer Oort cloud, the spherical shell loosely bound and easily rattled, from an inner, denser, donut-shaped region called the Hills cloud, beginning perhaps 2,000 astronomical units out. The outer shell is so weakly held by the distant sun that the galaxy itself interferes with it. The slow tide of the Milky Way's gravity and the occasional shoulder brush of a passing star are what tip Oort cloud bodies off their ancient shelves and send them falling toward the sun as the comets we eventually name. Every great comet in history, every omen that frightened emperors and decorated medieval chronicles, was a delivery from this address, dislodged by the traffic of the galaxy tens of thousands of years before anyone below noticed a new light in the sky. Think about what a first-pass comet actually is, and the cloud becomes almost tender. Some comets arrive on orbits indicating they have never visited the inner solar system before, ice assembled at the solar system's founding, stored at a few degrees above absolute zero for 4.5 billion years, untouched. When such a comet finally rounds the sun and grows its tail, sky watchers on Earth are looking at construction material older than any rock on our planet, making its first and often only appearance. The cloud mails us samples of itself, one every few years, across a gulf its senders will never see crossed in the other direction. We cannot go to the archive. The archive occasionally, carelessly, sends a page. The cloud's origin story connects it, unexpectedly, to the planet 2 entries back. The Oort cloud is construction debris, and the crane that threw it there was Jupiter, with help from the other giants. In the solar system's first few 100 million years, the region between the young planets swarmed with icy leftovers, and close encounters with the giants' gravity flung them outward by the billions. Most escaped entirely, lost to interstellar space, a fact worth pausing on, since it means our solar system has been seeding the galaxy with comets for 4.5 billion years, and other systems have been doing the same, which is part of why interstellar visitors like the 1-2 entries ahead were always expected eventually. The bodies that did not quite escape, slowed at the top of their arcs and circularized by the galaxy's tides, became the Oort cloud. The shell that marks the solar system's edge is made of the inner solar system's exiled construction scraps, thrown to the fence line by the planet whose interior we cannot enter, and left where no probe of ours will arrive intact and alive. One more thought completes the picture, and it dissolves a boundary rather than drawing one. If other stars keep Oort clouds of their own, and there is every reason to think they do, then those clouds are as oversized as ours, and the arithmetic becomes suggestive. Our cloud may reach 1.5 light-years outward. The nearest star lies just over 4 light-years away. If Proxima Centauri and the Alpha Centauri pair hold a comparable shell, then the outer wisps of their cloud and the outer wisps of ours may very nearly interleave, 2 fences of ice meeting in the dark, the property line between solar systems drawn not as a gap, but as a mingling. The edge of our solar system may quietly touch the edge of the next one, in a border region no light illuminates, patrolled by nothing, visited by nothing, where the sun and its nearest neighbor trade frozen debris across a fence neither will ever see. One small body, though, has made the crossing in the other direction, inbound, in front of our telescopes, within living memory. It came from another star entirely. It passed through our sky in a matter of weeks, and it is now leaving forever. It is the next entry on the list. Number 14, Oumuamua, the place that is leaving forever. On the morning of October 19, 2017, an astronomer named Robert Werrick was reviewing the night's images from the Pan-STARRS survey telescope on the summit of Haleakala in Hawaii. Among the moving points of light, one was moving wrongly. Its path was not an ellipse around the sun, the closed loop that binds every planet, asteroid and comet we had ever catalogued. Its path was a hyperbola, an open curve, the signature of an object that fell in from interstellar space and would leave the same way. Werrick had found the first confirmed visitor from another star system in the history of astronomy. It was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The visitor rewarded attention with confusion. Its brightness rose and fell by a factor of 10 every several hours, implying a shape unlike anything in our catalogues, perhaps 10 times longer than it was wide, a cosmic splinter tumbling end over end roughly every 8 hours. It reflected light like weathered rock or metal, slightly reddened by cosmic radiation. And it showed no tail. A comet arriving from such cold, approaching the sun, should have flared with escaping gas and dust. Oumuamua stayed stubbornly bare, so dark and quiet that the Spitzer Space Telescope, pointing at its position, saw nothing at all. Then came the detail that turned a curiosity into a genuine mystery. In June 2018, a team led by Marco Micheli confirmed from tracking data that Oumuamua was accelerating as it departed, gently but unmistakably, beyond what the sun's gravity allowed. Comets accelerate this way when escaping gas pushes them like a weak rocket, but no gas had been seen. The proposals since then span the respectable and the provocative. Perhaps it vented hydrogen, which telescopes cannot easily see. Perhaps it was an iceberg of frozen hydrogen, or a shard of frozen nitrogen broken off a Pluto-like world around another star. Perhaps it belongs to the newly recognized family of dark comets, which accelerate without visible tails. And the Harvard astronomer Avi Loeb argued, deliberately provocatively, that a thin artificial light sail would match the data as well. No hypothesis has won. The object gave humanity a few weeks of measurements and then withdrew beyond the reach of every instrument, leaving a permanent asterisk in the catalogue. Here is why a tumbling splinter counts as a place on this list. Oumuamua is a solid body, hundreds of meters long. In principle, a spacecraft could land on it, anchor to it, and ride it out of the solar system. It is a destination, and it is running away from us at about 26 kilometers per second of surplus speed, roughly 5.5 astronomical units per year, 5.5 times the Earth-Sun distance every year, forever. By the 2030s, it will be farther out than Neptune. In about 10,000 years, it will leave the Sun's gravitational neighborhood entirely, and hundreds of thousands of years from now, it will drift past other stars, carrying whatever answers it holds sealed inside it. And this is the entry with the ache in it, because Oumuamua may be the one place on tonight's list that is only almost unreachable. A research group called the Initiative for Interstellar Studies has spent years on a design effort named Project Lyra, publishing peer-reviewed trajectories for a chase. The mathematics works. A probe launched even in the late 2020s or 2030s, slinging past Jupiter or diving close to the Sun for a powered boost, could catch Oumuamua after a flight of roughly 22 years. The physics permits it. The engineering is ambitious but not absurd. What is missing is a decision and money. No agency has funded the chase, and every year of hesitation adds years to the pursuit, because the destination adds more than 800 million kilometers to its lead annually. So the first confirmed piece of another solar system, the first object we could ever have touched that formed around a different star, is departing at a walking pace by cosmic standards, slow enough to catch, fast enough that the window is closing. Future generations may reasonably ask why the species that could chase it chose not to. They will not be able to unmake the choice. The visitor does not wait, and it does not return. The few weeks of observation were a scramble worth remembering. Oumuamua was discovered already outbound, 40 days past its closest approach to the Sun, already dimming fast, and the world's major observatories dropped their schedules to chase it. The Very Large Telescope in Chile, the Gemini and Keck telescopes in Hawaii, the Hubble Space Telescope, all tracked the fading point as long as instruments allowed, and radio projects, including the Breakthrough Listen initiative, pointed dishes at it and heard exactly nothing, a silence worth recording given the speculation to come. By January 2018, it was beyond the reach of even Hubble. The complete scientific record of the first interstellar visitor, every measurement humanity will ever possess, was gathered in about 11 weeks. Rarely has so much analysis rested on so brief an acquaintance. Two later visitors sharpened, by contrast, how strange the first one was. In August 2019, an amateur astronomer in Crimea named Gennady Borisov discovered the second interstellar object, and it behaved with almost disappointing normality, a comet like our own comets, tailed and well-mannered, as if to prove the doorway Oumuamua used was real and ordinary. A third visitor followed in 2025, larger and older, plausibly older than the solar system itself. Neither resembled the first. No tail, no coma, tumbling, accelerating, shaped like nothing in the catalogues. Oumuamua remains the anomaly of its own category, the founding member of a class it does not fit. The Rubin Observatory's decade-long survey is expected to find interstellar visitors routinely, perhaps dozens, and every one will be checked, quietly, against the strange first one that got away. And if Project Lyra, or some successor, ever does fly, the reward would be unlike any mission in history. A lander on Oumuamua would be sampling a piece of another planetary system, shaped around another star, sandblasted by hundreds of millions of years of interstellar radiation, a free sample of elsewhere delivered to our doorstep and now departing. The chase would take longer than most careers, and the encounter, at those closing speeds, would demand extraordinary engineering merely to linger. But the alternative is what this entry records. The first messenger from another star will spend the next 100,000 centuries crossing the dark with its answers on board, unread. Some unreachable places are built by physics. This one is being built year by year by the quiet arithmetic of postponement. The visitor's name and pedigree carry their own quiet poetry. The designation is 1I, the first object of a new class the naming authorities had to invent on the spot, interstellar. The name itself was proposed by Hawaiian language and culture experts consulted by the Discovery team, and it fits with uncanny precision, a messenger from afar arriving first. As for where it came from, dynamicists ran its trajectory backward and found it entered the solar system from roughly the direction of the star Vega in the constellation Lyra, but the honest answer is that its home cannot be identified. It has been adrift so long, by most estimates hundreds of millions of years and possibly billions, that every candidate home star has itself moved far from wherever the ejection happened. Oumuamua is not merely from another solar system. It is from another era of the galaxy, launched before complex life existed on Earth, orphaned so thoroughly that even its birthplace no longer marks the map. When it passed through our sky, the encounter joined two histories that had been separated for a substantial fraction of the age of the galaxy, for 11 weeks once. The physical encounter, had we been ready for it, was almost insultingly convenient by the standards of this list. At its closest, Oumuamua passed within about a quarter of the distance between Earth and the Sun, nearer than Mercury ever comes to us, close enough that a prepared spacecraft, parked and waiting, could have reached it in weeks. The visitor did not merely enter the solar system. It threaded the inner system, sweeping past our star at a range our probes cross routinely. The unreachability of this entry is therefore unique in the countdown, a matter not of where the place is, but of when we were. It arrived a few decades before our species maintained the readiness to greet such things, and the galaxy is under no obligation to schedule its deliveries for our convenience. The Rubin Observatory era may fix the readiness. Nothing can reschedule the first delivery. Oumuamua came from the direction of other stars. The nearest of those stars, as it happens, keeps a world of its own, a rocky planet in the temperate zone, the closest world beyond our solar system. We can measure its year, its mass, and its star's weather. It is the next entry, and no one alive will ever see it up close. Number 13, Proxima Centauri b, the nearest world we cannot visit. The closest star to the Sun is a dim red dwarf called Proxima Centauri, 4.24 light-years away. In astronomical terms, that is next door. In human terms, it is about 40 trillion kilometers, and the gap between those two sentences is the whole subject of this entry. In 2016, a team led by Guillem Anglada Escud ran a campaign they called Pale Red Dot, watching Proxima Centauri night after night with a precision spectrograph in Chile, looking for the tiny rhythmic wobble a planet's gravity imposes on its star. In August of that year, they announced the result. Proxima Centauri has a planet, at least 1.1 times the mass of Earth, circling once every 11.2 days. That orbit sounds scorchingly close, and it is, only about 1/20th of the Earth-Sun distance. But Proxima is so dim, with about 1/8 of the Sun's mass, that this close-in track lies within the habitable zone, the band where a world with an atmosphere could keep liquid water on its surface. The nearest star to home keeps a roughly Earth-mass planet in its temperate zone. When the news broke, it read like an invitation. Then comes the arithmetic, and the invitation quietly withdraws. Voyager 1, our fastest deep space veteran, would need about 73,000 years to cover the distance to Proxima, had it been aimed there. 73,000 years ago, humans had not yet painted the caves of Europe. The Parker Solar Probe, the fastest machine our species has ever built, briefly touches 692,000 kilometers per hour near the Sun. Even at that pace, sustained impossibly forever, the trip would take more than 6,000 years. Chemical rockets, the technology that took us to the Moon, simply do not speak the language of interstellar distance. One serious proposal exists on paper. In 2016, the Breakthrough Starshot Initiative announced a $100 million study of a different approach entirely. Build a ground array of lasers with a combined power around 100 gigawatts. Launch swarms of probes the size of postage stamps, each weighing about a gram, each attached to a light sail a few meters across. Fire the laser array at each sail for a few minutes, accelerating it to 20% of the speed of light. At that speed, the crossing to Proxima takes about 20 years, plus 4¼ years for the radio postcard home. Nothing in physics forbids it. Everything in engineering currently defers it. The laser array does not exist, the gram-scale probes do not exist, and a sail that survives the beam does not exist. Most estimates place such a mission generations away, and it would deliver, at best, a few blurry frames from a flyby lasting seconds. A crewed voyage is not on any horizon at all. For every human being now alive, Proxima b is a fact and not a destination. The world itself, meanwhile, guards its own mysteries. Proxima Centauri is a flare star, prone to sudden eruptions. In 2017, the ALMA Observatory recorded a flare that briefly made the little star roughly 10 times brighter at some wavelengths, and such events, repeated over billions of years, may have stripped away Planet B's atmosphere entirely or sterilized its surface with radiation. Because the planet almost certainly keeps one face permanently toward its star, it may be what astronomers call an eyeball world, a hemisphere of glare fading through a ring of twilight into a hemisphere of ice. Whether it holds air, water, or anything else is unknown, and settling the question may itself take a generation of new telescopes. The star itself was found by a measurement of exquisite patience. In 1915, the Scottish-born astronomer Robert Innes, working in South Africa, identified a faint red star that shared the motion of the bright Alpha Centauri pair, and follow-up parallax work confirmed it as fractionally the nearest of the three, earning it the name Proxima. It belongs to a triple system. Alpha Centauri A and B are two sun-like stars circling each other closely, while little Proxima loops around the pair on an orbit so wide it takes roughly 500,000 years, so distant from its bright companions that from a vantage near them it would be just another dim red dot. The nearest stellar system to home is thus three destinations in one, and the nearest single doorstep of the three belongs to a star too faint to see with the naked eye, despite being, cosmically speaking, in our front garden. The detection method rewards a moment of appreciation because nobody has ever actually seen Proxima b. The planet announced itself as a rhythm. Its gravity swings its star in a small circle, and that swing shifts the star's light alternately toward blue and red as the star approaches and retreats, a cycle repeating every 11.2 days at an amplitude that corresponds to the star drifting about walking pace. The pale red dot team measured a wobble of roughly 5 kilometers per hour, a stroll, in a star 25 million kilometers away, and pulled from it a planet's existence, minimum mass, and year. Later analyses added evidence for at least one more planet in the system, a candidate cold world on a wider orbit, and a possible small inner companion, making Proxima not just a star with a planet, but a planetary system, the nearest one there is. What the next decades can honestly deliver is sight, not arrival. The coming generation of ground telescopes, led by the extremely large telescope under construction in Chile with its 39-meter mirror, has Proxima b on its target list for direct imaging, the separation of the planet's faint reflected light from its star's glare. Within the lifetimes of most people hearing this, humanity may possess a genuine photograph of the nearest exoplanet, perhaps even a crude reading of its atmosphere, oxygen or water vapor or nothing at all. Each such measurement will arrive 4 years and 3 months old, carried at the only speed the universe honors. The neighbor's porch light is visible from ours. The path between the porches is the thing the universe declined to build. One further fact reframes the whole relationship, and it concerns time rather than distance. Proxima Centauri is a red dwarf, and red dwarfs are the misers of the stellar economy, burning their fuel so slowly that they outlive every other kind of star. Our Sun has perhaps 5 billion good years remaining. Proxima's projected lifespan runs to trillions of years, hundreds of times longer, so far beyond the Sun's that the comparison barely passes. When the Sun has swollen, shed its outer layers, and collapsed into a cooling white dwarf, Proxima will still be quietly burning, barely changed, with most of its life still ahead of it. If Proxima b survives its star's youthful temper, it will still be orbiting, still keeping its temperate distance, long after our solar system's story has ended. The nearest world we can never visit is also, in the long accounting, the more permanent address. The unreachable neighbor will outlast the reachable home, which gives the 4 light-years between them a strange direction. We are not the mainland looking at an island. We are the island. And the 4-year signal gap deserves to be made concrete before this entry closes, because it defines the best relationship our species can ever have with the place. Suppose some future observatory detects an unambiguous signature in Proxima b's atmosphere, and suppose, against every current expectation, something there ever signaled. The tightest possible conversation would run at 8.5 years per exchange, a question asked by one generation of scientists and answered into the notebooks of the next. Even our accidental introduction is already en route and cannot be recalled. The radio and television leakage of the 20th century swept past Proxima decades ago, and the sphere of our loudest broadcasts is now over 100 light-years wide, expanding at the only speed the universe honors. Whether anyone is there to notice or not, the nearest unreachable world has already heard from us, in the only form of visiting we will ever manage, and it took our messengers 4 years and 3 months to make a trip no messenger of flesh will ever begin. So consider what Proxima b actually is, on a list like this one. Its light reaches us in 4 years and 3 months. A reply, if anyone were there to send one, could complete a round trip within a decade. By every measure of information, it is a neighbor. By every measure of travel, it is unreachable within any human lifetime, and perhaps within any human century. It is the gentle case, the minimum distance the universe charges for a visit to another living room, and the price is 70,000 years, cash. Farther out in the catalogue, the terms only get worse, and the next entry shows how much worse, on a world where the nightly forecast is molten metal. Number 12, the night side of WASP 76b, where it rains iron. Some 640 light-years away, in the constellation Pisces, there is a world where the weather report has been the same for 1 billion years, and it reads, molten iron rain after dusk. The planet is called WASP 76b, first flagged in 2013 by the WASP Transit Survey, a network of small robotic cameras watching for stars that dim slightly when a planet crosses in front of them. It is a giant, about 9/10 the mass of Jupiter but puffed by heat to nearly twice Jupiter's width, and it hugs its star so closely that its year lasts 1.8 days. At that range, the star's gravity has locked the planet's rotation, so one face endures permanent day while the other faces permanent night. The day side is the furnace. Temperatures there rise beyond 2,400 degrees Celsius, hot enough not merely to melt iron, but to boil it into vapor, so the daytime sky of WASP 76b literally contains gaseous metal. Winds far faster than any hurricane then carry that iron vapor around the planet toward the night side, where the temperature falls to a comparatively mild 1,500 degrees. And at the boundary, along the line where day hands over to night, the iron condenses. Droplets of liquid metal, glowing with their own heat, fall through alien clouds. Somewhere on that boundary, right now, it is raining iron. The way we know this deserves its own admiration. In March 2020, astronomers using the espresso spectrograph on the Very Large Telescope in Chile split the planet's light finely enough to detect iron vapor at the planet's evening edge, where day rotates into night, but not at the morning edge, where night rotates back into day. The iron enters the night side as vapor and never comes out the other side as vapor. Somewhere in the dark, it rained out. Later observations added detail upon detail. The Cheops Space Telescope caught signs of a glory, a rainbow-like ring of light scattered by uniform droplets, a phenomenon known from Earth's own clouds. Other teams found barium high in its atmosphere, an element so heavy that its presence in the upper sky remains unexplained. We have assembled the meteorology of a world no camera has ever resolved as more than a dip in starlight. As a destination, WASP 76b is sealed 3 times over. It lies 640 light-years away, 150 times the distance to Proxima, which alone banishes it beyond every conceivable vehicle. Its day side vaporizes the alloys spacecraft are made of, and its night side, the merciful side, offers crushing gravity, perpetual dark, and precipitation that would slice through a hull like hot shrapnel. It stands on this list as the representative of an entire modern genre, the thousands of catalogued worlds whose weather we can read from Earth, while their ground remains permanently unwalkable. We are becoming a civilization of meteorologists for places we will never enter. The instrument behind the discovery is a study in modest means. The WASP survey, short for Wide-Angle Search for Planets, was not a great observatory but an array of commercial camera lenses, 8 to a mount, photographing wide fields of sky from the Canary Islands and South Africa, hunting for stars that dimmed by about 1% on a repeating schedule. That 1% is a planet crossing its star's face. WASP's unglamorous hardware has found nearly 200 worlds this way, and WASP 76b announced itself as exactly such a flicker, a star in Pisces, dipping every 1.8 days. Everything since, the iron rain included, has been extracted from starlight alone, and the extraction technique is lovely. When the planet crosses its star, a thin ring of its atmosphere is backlit, and the atmosphere's atoms bite characteristic notches into the passing light. Read the notches, and you have a chemical inventory of air 640 light-years away. Read how the notches shift during the crossing, and you can clock the planet's winds, and even tell its evening from its morning. Meteorology at 100 parsecs, from a rack of camera lenses and a very large mirror. The planet's broader class makes the forecast even stranger. WASP-76b belongs to the ultra-hot Jupiters, giant worlds parked so close to their stars that their atmospheres cross into chemistry no planet in our solar system approaches. On the day side of such a world, the heat is sufficient to tear ordinary molecules apart, water included, into their component atoms. Carried around to the night side, the fragments cool and recombine, so the planet is perpetually disassembling its own atmosphere on one hemisphere and reassembling it on the other, a chemical tide with no shore. Iron is simply the most photogenic passenger in that circulation. Later studies of this planet's twin worlds have reported clouds whose condensates may include corundum, the mineral of rubies and sapphires, and on the very hottest of the class, atmospheres containing vaporized rock. Nature, given a wide enough catalogue, will run every experiment. And the night side itself, the destination this entry names, would be a place of upside-down beauty. No star ever shines there, and yet it is not dark. The ground and clouds glow dull red with their own 1500-degree heat, like the inside of a kiln with the door shut. The rain, where it falls, would be luminous, threads of molten metal dropping through red murk toward an interior with no floor, evaporating again as they sink into rising heat. It is weather as a closed loop, iron boiled on the day side, rained on the night side, and carried back around to boil again, a cycle that has repeated without witness for billions of years and will continue without witness for billions more. We know the forecast precisely. The window it describes can never have a face at it. The distances involved earn one more turn of the screw, because even seeing this planet is an act of reconstruction across time. The light carrying tonight's forecast, iron rain at the evening border, left WASP-76b around the 14th century, while plague crossed Europe and no instrument on Earth could magnify anything. Its weather report arrives 640 years stale, which by the standards of this list is practically current affairs, and everything we will ever learn about the place will arrive on the same delay. If some observatory of the 23rd century watches the planet's iron clouds shift, it will be reading weather that happened before telescopes existed. The planet, meanwhile, will not last forever in its current form. Worlds parked that close to their stars are slowly boiled, their atmospheres stripped particle by particle, and on timescales of billions of years, WASP-76b may be reduced toward its core. The forecast is permanent only by human measures. On the universe's clock, even the iron rain is a passing shower, and we are catching it, from 640 light-years away, in the brief age when it falls. Yet even molten rain is, in the end, only weather, a symptom of a place, rather than its essence. The next entry removes the veil of atmosphere entirely. It has a true surface, solid ground you could in principle point to, and that ground is the most forbidden solid surface in the known universe. Number 11. The surface of a neutron star. When a star much larger than the Sun exhausts its fuel, its core collapses in less than a second, and the collapse forges the densest stable object nature permits, a neutron star. The recipe is simple to state and impossible to picture. Take about 1.5 times the mass of the Sun. Compress it into a sphere roughly 20 to 25 kilometers across, the size of a city. The result is matter at the density of an atomic nucleus, a substance so concentrated that a single teaspoon of it would weigh several billion tons, more than every automobile on Earth combined, pressed into the bowl of a spoon. These are not theoretical objects. Thousands are catalogued, many as pulsars, spinning beacons whose radio flashes sweep past Earth with clock-grade regularity. NASA maintains an X-ray telescope called NICER on the International Space Station largely to study them, and its measurements of one heavyweight example, a pulsar called J0740 found about 2.1 solar masses packed into a diameter near 25 kilometers. 2 suns' worth of matter would fit inside the ring road of a mid-sized city. Some spin at rates that defy intuition. The fastest known, discovered in 2005, rotates 716 times every second, its equator moving at nearly a quarter of the speed of light. A body the size of Manhattan, spinning faster than a kitchen blender, has been verified by multiple observatories. Now consider the surface as a place, because it is one. A neutron star has a crust, believed to be a crystalline lattice of exotic nuclei, an actual solid landscape. It may have mountains, and here the numbers turn eerie. Gravity at the surface runs 100 billion to 200 billion times stronger than Earth's, and gravity that strong permits no tall structures of any kind. Calculations suggest the highest mountains on a neutron star stand a few millimeters tall, and supporting even that requires the strongest material in the universe, the crust itself, billions of times stronger than steel. A world with terrain, where the terrain is measured in millimeters, under a sky of permanent starlight. Approach is impossible at every stage, and the failure modes escalate elegantly. Thousands of kilometers out, tidal forces become the problem. The difference in gravitational pull between the near and far ends of any approaching spacecraft would stretch it, then tear it apart, well before arrival. For the magnetized variety called magnetars, whose fields reach 1,000 trillion times Earth's, a new barrier appears around 1,000 kilometers out, where the magnetic field itself deforms atoms, stretching electron orbitals into needles, so that chemistry as we know it stops working. Any matter that somehow completed the landing would not land in any meaningful sense. It would be flattened instantly into a film of degenerate matter, far thinner than an atom, its identity as a spacecraft, or as anything, erased. Standing is not a concept the surface supports. And below the crust, the interior descends through phases physicists have playfully named nuclear pasta, matter kneaded by pressure into sheets and tubes, toward a core whose true state remains one of the open problems of physics. The nearest known neutron stars lie a few hundred light-years away, but for once, the distance is beside the point. Every other destination so far has been unreachable because we cannot get there. A neutron star's surface is unreachable because there is no version of arriving. The universe builds solid ground on which standing itself is forbidden, and it builds that ground by the thousand. The existence of such objects was predicted with almost indecent speed. The neutron itself was discovered in the laboratory in 1932, and within 2 years, the astronomers Walter Baade and Fritz Zwicky proposed that the explosive deaths of massive stars, which they named supernovae, would leave behind stars made almost entirely of neutrons, packed to nuclear density. It was an idea decades ahead of any possible test, and it waited patiently until 1967, when a Cambridge graduate student named Jocelyn Bell, reviewing kilometers of chart paper from a radio survey she had helped build, noticed a bit of scruff, a signal pulsing every 1.3 seconds with unnatural regularity. The team half-jokingly labeled it LGM-1 for Little Green Men, before more such sources turned up across the sky and the natural explanation crystallized. The pulses were lighthouse beams from spinning neutron stars, Baade and Zwicky's prediction broadcasting proof of itself across the galaxy. It stands among the great vindications in science, and the detection earned a Nobel Prize, awarded controversially to Bell's supervisor rather than to Bell, a piece of history the field has been reckoning with ever since. The precision of these objects is its own form of the uncanny. The most stable pulsars keep time so well that their pulses, monitored for years, rival atomic clocks, and astronomers now use networks of them as a galaxy-sized timekeeping array. Yet the same objects also misbehave in ways that reveal their solid nature. Occasionally, a pulsar's spin abruptly jumps, an event called a glitch, and the leading explanation is a starquake or an internal slip, the crust of the star fracturing or the superfluid interior lurching against its container. When a neutron star's crust shifts by a fraction of a millimeter, observatories on Earth notice. A landscape where a millimeter of tectonics is a cataclysm visible across thousands of light-years is not a landscape in any sense a boot could ever test. There is also a version of this destination that raises the stakes even further, and it belongs here as the extreme of the extreme. Some neutron stars, the magnetars, carry magnetic fields 1,000 times stronger even than ordinary pulsars, and their tantrums are visible across the galaxy. In December 2004, one such object on the far side of the Milky Way released a flare that, in a fifth of a second, outshone in gamma rays what the Sun releases in 250,000 years, and it measurably compressed Earth's ionosphere from 50,000 light-years away. A place that can slap our planet's upper atmosphere from across the galaxy does not need to explain why visitors are not received. The surface of a neutron star is the one landscape in this countdown that enforces its own unreachability with active violence, at every distance, in every direction, all the time. History has even recorded the birth of one of these objects, though nobody watching knew it at the time. In July of the year 1054, Chinese court astronomers logged a guest star in the constellation we call Taurus, a light so bright it was visible in daytime for over 3 weeks, and chroniclers in Japan and the Arab world noted it as well. That guest star was a supernova, the collapse of a giant star's core, and the collapse manufactured a neutron star. We can point a telescope at the address today and find the Crab Nebula, the still expanding wreckage of the explosion, and at its center, the Crab Pulsar, spinning 30 times per second, sweeping the debris with beams of radiation like a lighthouse in a demolished harbor. 1,000 years separate the astronomers who saw the flash from the astronomers who identified what the flash built, and the two groups belong to the same continuous project. Somewhere in the records of the 11th century is an eyewitness account of the construction of a place in tonight's countdown, filed by people who could not have imagined what they were witnessing, preserved for the people who could. The interior, below the untouchable surface, may hold the strangest matter in existence, and physicists study it precisely because it cannot be made on Earth. A neutron star is in effect a single atomic nucleus the size of a city, held together by gravity instead of nuclear force, and the deeper you model it, the stranger the phases become, from the crystalline crust through the tangled shapes of nuclear pasta to a core that may contain matter dissolved into its constituent quarks. No laboratory can hold material at such densities for even an instant. So the objects themselves have become the laboratory, read from afar. When two neutron stars collided in 2017, gravitational wave detectors on Earth felt the space around us quiver, and the way the two bodies deformed each other in their final orbits carried information about the stiffness of their interiors, physics at densities forever beyond human manufacture, delivered by the shudder of space-time itself. The most forbidden surfaces in the universe conduct seminars, and attendance, from 100 million light-years away, is free. From ground no one can stand on, the list now rises to the towers everyone has seen, the most famous photograph in the history of astronomy, and the halfway mark of our descent. Number 10. The Pillars of Creation. We have reached the middle of the list, and it is worth pausing on the climb so far. We began a few hundred kilometers behind your own head, at the point in space you abandoned by existing. We passed through the sealed furnace at the center of our star, rode a dying probe into Jupiter, stood on Sedna's red ice 5 light days from the Sun, and searched for a planet nobody can find. We watched 5 dead ships drift toward a shell of ice they will take 300 centuries to cross, said goodbye to an interstellar visitor we chose not to chase, and priced a trip to the nearest neighboring world at 73,000 years. We have covered, in the scheme of tonight's list, almost no distance at all. Everything so far has been local. The second half of the countdown leaves the neighborhood, and it begins with 3 towers of dust that decorate half the textbooks on Earth. In April 1995, 2 astronomers, Jeff Hester and Paul Scowen, aimed the Hubble Space Telescope at a small corner of the Eagle Nebula, a star-forming cloud 6,500 to 7,000 light-years away in the constellation Serpens. The image that came back became, by most reckonings, the most famous astronomical photograph ever taken. 3 columns of cold gas and dust rise against a glowing background, sculpted, backlit, and impossibly tall. NASA named the picture the Pillars of Creation, and for once, the grandeur of the name undersold the subject. The tallest pillar stands roughly 4 to 5 light-years high. Translated, that is around 40 trillion kilometers of tower, hundreds of millions of times the height of Everest. The entire distance from the Sun to Proxima Centauri, the gulf we just priced at 73,000 years of travel, would fit inside that single column of dust standing on end. The pillars are not monuments. They are a construction site. Inside their fingertips, gravity is condensing knots of gas into new stars, and the towers themselves are being simultaneously carved and destroyed by the ultraviolet glare of a cluster of massive young stars called NGC 6611, burning just off the top of the frame. The same radiation that shapes the pillars is evaporating them, boiling their material away in a process astronomers call photoevaporation. The sculpture and the sculptor's chisel are the same light. Drift beside them for a moment, a light-year out. The towers fill half the sky, rims glowing where starlight grazes them, interiors black as basalt. Their edges do not hold still. Wisps the size of our entire solar system peel away in slow motion, streaming like smoke in a wind of ultraviolet light. Here and there along the columns, small dark knots hang like fruit, each one a solar system in the making, each one large enough to swallow every orbit in ours. At the fingertip of the tallest pillar, a buried newborn star lights its cocoon from within, a lantern inside a fist of dust. Nothing moves at any speed your eye can register, and everything is moving, thousands of kilometers per hour, frozen by sheer scale into stillness. Now for the rumor, because this entry carries one, and it is instructive. In 2007, observations from the Spitzer Space Telescope revealed a region of surprisingly warm dust near the pillars, and one interpretation ran ahead of the data. The warmth, some argued, was the shockwave of a recent supernova, and headlines around the world announced that the pillars of creation had already been destroyed, that because their light takes millennia to reach us, we were admiring ghosts, towers that no longer existed. The story had everything: poetry, doom, and cosmic irony. It was also, on later inspection, wrong. Further analysis found the warm dust better explained by the radiation of the massive stars themselves. No supernova remnant appears where one should. And when the James Webb Space Telescope re-imaged the pillars in October 2022, in infrared detail that pierced the dust, the towers stood intact, still forming stars, still slowly eroding. The honest label on this entry reads, "Not destroyed, dissolving on schedule, with an expected lifetime around 3 million more years against the patient sandblasting of starlight." But notice what the false alarm taught, because it is the real cargo of this entry. For those few years, humanity genuinely did not know whether the most photographed structure in the sky still existed, and there was no way to check. There is still no way to check. Every image of the pillars shows them as they were roughly 65 centuries ago, around the time humans were inventing writing. Their present tense is simply not available to us, and never will be. A probe dispatched at Voyager speed would need more than 100 million years to make the trip, and it would arrive to find the towers reshaped or gone, because this destination has a shorter life expectancy than the journey. The words "already gone" hung over the pillars for a decade as a rumor. Hold on to those words. At the end of this list they return, not as a rumor, but as arithmetic. The photograph itself has a redemption story folded into it. When Hubble launched in 1990, its main mirror turned out to be flawed, ground exquisitely precisely to the wrong shape, and for 3 years, the world's most famous telescope was a punchline, delivering blurred images. In December 1993, astronauts installed corrective optics in orbit, and the observatory's second life began. The pillars image arrived 16 months later, and it did more than any technical report to announce that the repaired Hubble worked. It ran on front pages around the world, entered classrooms and album covers and postage stamps, and became, for a generation, the default mental picture of what the universe looks like. It is worth remembering that this icon was very nearly a blur. The most seen place in the distant sky owes its fame to a service call 300 miles overhead. The structures themselves reward a closer look than the famous image usually gets. The pillars survive because their tips are armored. Each column is capped by a dense knot of gas, whose shadow protects the length behind it, the way a boulder on a beach leaves a tail of sand as the tide strips everything unprotected. Studded along the columns, Hubble revealed dozens of small dark blobs that astronomers named evaporating gaseous globules, each one a would-be solar system racing to finish its collapse before the ultraviolet flood strips away its raw material. Star formation here is not a gentle condensation. It is a footrace between gravity pulling inward and radiation peeling away, and many of the racers lose, left as stunted objects when their cocoons burn off too soon. Every star born in the pillars is a photo finish, and our own sun, 4.5 billion years ago, likely won exactly this kind of race in a nebula long since dissolved. The picture has also become a time-lapse without anyone intending it. When Hubble re-imaged the pillars for its 25th anniversary in 2015, comparison with the 1995 frame showed measurable change. A jet from a newborn star inside had lengthened visibly in 20 years, streaming farther into space at hundreds of thousands of kilometers per hour. The James Webb image of 2022 added hundreds of previously hidden newborn stars glowing red inside the dust, and lava-colored ridges of shocked gas where infant stars are firing their tantrums into the columns. Set side by side, the images bracket a single generation of human life, and they show the towers actively working, forming suns in real time. The pillars are not a monument we are watching decay. They are a factory we are watching produce, from a distance of 6,500 years, on a delay we can never shorten. There is a version of this entry that touches us directly, and it is easy to miss inside the famous image. The Sun formed in a place exactly like this. 4.5 billion years ago, our star condensed inside some dense knot of a star-forming nebula, one warm fingertip among hundreds, in a cloud carved and lit by massive neighbors, and the evidence survives in our own solar system's chemistry, traces of short-lived radioactive elements in ancient meteorites that only a nearby massive star, or its supernova, could have delivered fresh. That nursery is gone. Star-forming clouds are temporary by nature, dispersed within a few tens of millions of years by the very stars they make, and the Sun's siblings, the hundreds or thousands of stars born from the same cloud, have long since scattered around the galaxy's disk, unrecognizable among the crowd, though astronomers have tried to identify a few by their chemical fingerprints. Which yields this entry's quietest turn. The pillars of creation are a photograph of our own kind of birthplace, and our actual birthplace no longer exists anywhere. The first landscape every star calls home is one that no star, and no traveler from any star, can ever revisit, because the address itself has been dissolved and reabsorbed into the galaxy. Even the universe's residents cannot go home again. The towers in the picture are somebody's future memory, already on schedule to vanish. The cluster doing the sculpting adds a note of foreshadowing worth keeping. The stars of NGC 6611 are young, 1 million or 2 years old, and the brightest of them are of the short-lived giant kind, stars that spend their fuel in a spendthrift few million years and end as supernovae. Sooner or later, one of the pillar's own neighbors will detonate in earnest, and a real shockwave, not the rumored one of 2007, will sweep the towers away for good. The false alarm from Spitzer was wrong about the past, but it was, in all likelihood, a preview of the future. The reprieve the James Webb image documented is a reprieve, not a pardon. Every part of this scene, the towers, the cluster, the glowing gas, is a single frame of a firework, and we happen to be the generation holding the frame. The pillars decorate one small corner of one spiral arm of our galaxy. At that galaxy's center, 26,000 light-years from your bed, waits the one address that every star you have ever seen is quietly obeying. Number 9. Sagittarius, a star, the heart of the Milky Way. Behind the star clouds of the constellation Sagittarius, low in the summer sky, sits the center of everything you have ever watched rise and set. The Milky Way pivots around a single point, and at that point sits a supermassive black hole called Sagittarius A star, holding about 4.3 million times the mass of the Sun within a region smaller than Mercury's orbit. The distance from here to there is about 26,000 light-years, give or take a few hundred, which means the light arriving from the galactic center tonight left home while Ice Age hunters were crossing frozen plains toward continents without names. We have photographed this place. On May 12, 2022, the Event Horizon Telescope collaboration released the image, assembled by linking radio dishes across the planet into a virtual instrument the size of Earth itself. The picture shows a glowing, uneven ring of superheated gas orbiting a central shadow, the silhouette of the event horizon backlit by its own captive fire. The dot at the heart of every arrow on every map of the galaxy turned out to look exactly as general relativity said it would. Long before the portrait, we had the testimony of the stars that live there. For 3 decades, 2 teams, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in California, tracked individual stars whipping around the invisible point at the galaxy's core. One of them, called S2, dives within 120 astronomical units of the black hole every 16 years, reaching speeds near 3% of the speed of light, and its orbit obeys Einstein's equations to the decimal. Another, S4714, appears to graze even closer, touching roughly 8% of light speed, which makes it one of the fastest objects known. Watching stars, the massive suns get slung around like gravel, settled the question of what sits there. The precision of that work earned Genzel and Ghez the Nobel Prize in Physics in 2020. The neighborhood around the black hole is itself extreme, a nuclear star cluster packed 1 million times denser than our stellar suburbs, laced with 100-light-year magnetic filaments, giant molecular clouds, and a family of dust-shrouded objects, the G-objects, that stretch like taffy when they swing too near the center and somehow survive. The unreachability here is plain, brutal distance, but the numbers deserve their moment. 26,000 light-years, at the speed of Voyager 1, is a journey of roughly 450 million years. That is not a long time in the way centuries are a long time. When the light we now receive from Sagittarius A star has an age, our journey time has an era. 450 million years ago, nothing with a backbone had yet walked on land. A probe launched then, by whatever might have launched one, would be arriving about now. And even a magically instant light-speed craft changes nothing that matters, because the report home takes another 26,000 years, so the round trip exceeds the age of civilization several times over. The galaxy's downtown is closed to the galaxy's residents. Every star in the Milky Way, our Sun included, orbits this point. Not one of them, and nothing launched from any of them, can practically call on it. There is one more twist of perspective worth taking to bed. You have spent your entire life in orbit around Sagittarius A star. Every birthday, every commute, every night of sleep has traced 1/230 millionth of a single galactic year around a black hole you will never approach. The still point of our galaxy is also its most forbidden address, and the galaxy pays its respects only from a distance. The discovery of this place is a story about learning to see through a wall. In visible light, the galactic center is simply not there. 30 magnitudes of dust extinction stand in the way, meaning only about 1 photon of visible light in a trillion completes the trip, and the middle of our own galaxy went unseen for the whole history of astronomy before technology changed the terms. The first breakthrough came by accident in 1932, when a Bell Labs engineer named Carl Jansky, assigned to find sources of static, troubling transatlantic radio calls, discovered a hiss that peaked when his antenna faced Sagittarius. He had detected the center of the Milky Way and founded radio astronomy in the process, though the significance took years to sink in. In February 1974, the radio astronomers Bruce Ballack and Robert Brown finally pinned down the compact source at the exact dynamical heart of the galaxy, the bright point later named Sagittarius A star. Infrared astronomy then opened the second window, and by the 1990s, telescopes equipped with adaptive optics, mirrors that flex hundreds of times per second to cancel the atmosphere's blur, could watch individual stars in the crowded core, which is what made the great orbit tracking campaigns possible. Every fact we own about the galaxy's heart came through walls that stopped every astronomer before the 20th century from ever suspecting the heart existed. The orbit of the star S2 provided one of the cleanest tests general relativity has ever passed. In May 2018, the star swept through its closest approach at 7,700 kilometers per second, while the gravity instrument in Chile watched with fractions of a milliarc-second precision. The star's light, climbing out of the black hole's gravity, arrived measurably reddened, exactly as Einstein's equations demanded, and over subsequent years, the orbit itself was seen to rotate, tracing a slow rosette rather than a fixed ellipse, again on prediction. There is something satisfying in the symmetry. The most extreme ordinary object we can never visit is also the proving ground where our best theory of gravity, written a century ago in Berlin, keeps being checked and keeps passing by starlight measured across 26,000 light-years. One more layer completes the portrait, and it is a calm one. Black holes are engines of violence in popular imagination, and Sagittarius A star can flare, but on the whole our galactic center is remarkably quiet, a dim ember compared to the blazing quasar cores of active galaxies. Its accretion is a trickle. Some galaxies' central black holes outshine their entire host galaxy while feeding. Ours mostly fasts, flickering faintly as occasional wisps of gas fall in. The heart of the Milky Way, forbidden and extreme, is also, by the standards of its kind, gentle, a sleeping monster whose stillness is the reason the galaxy around it, and the listener falling asleep inside that galaxy, can afford to find it beautiful rather than fearsome. Try, briefly, the thought experiment of contact, because the numbers make it a meditation rather than a plan. Suppose we transmitted a message toward the galactic center tonight, aimed at whatever might orbit in the crowded inner light years. The signal crosses the Orion Arm, threads the star clouds of Sagittarius, and arrives at the center around the year 28,000. If something receives it and replies at once, the answer reaches Earth around the year 54,000. The total span, transmission to reply, is roughly 10 times the age of writing. Whatever entity might eventually decode the reply, it will not, in any meaningful sense, be us. On these scales, conversation is impossible, and even monologue becomes a relay between civilizations, each message a time capsule addressed to whoever happens to hold the receiving end when it arrives. The galaxy is not too big for signals. It is too big for exchanges, and the center of our own galaxy is already far into the territory where communication and archaeology become the same activity. And yet the center touches us continuously, which is the entry's gentle closing turn. The Sun's orbit around Sagittarius A star is what organizes our galaxy's disk, the frame within which every constellation drifts, and the black hole's mass, 4.3 million suns, is part of the gravitational architecture that has held the Milky Way's structure steady long enough for stars like ours to form, persist, and grow planets with continuous histories of billions of years. The forbidden address at the center is not a threat looming over the galaxy. It is closer to a keel. Every night of sleep anyone has ever slept has been spent in smooth, silent orbit around it, at 230 kilometers per second, on a track so stable that nothing in a human lifetime, or 100,000 human lifetimes, will measurably bend it. Unreachable and load-bearing. The galaxy is built around a room no one enters. Our galaxy circles its center, and our galaxy as a whole is itself in motion, bound for a rendezvous that astronomers spent a century calling inevitable. The neighbor it may be meeting is the next entry on the list, and it is the one unreachable place that might make the journey for us. Number 8. The Andromeda Galaxy. On a clear autumn night, far from city lights, you can find a faint, elongated smudge in the constellation Andromeda, visible to the naked eye if you know where to look. That smudge is the Andromeda Galaxy, also called M31, and it is the most distant object human eyes can see without help, about 2.5 million light-years away. The light entering your eye when you find it left Andromeda before the genus Homo existed. No human being was alive when tonight's Andromeda light began its trip, and every photon of it will have crossed 2.5 million years of emptiness to end its journey on a retina. Andromeda is the nearest large galaxy, a spiral like ours but bigger, a disk of perhaps 1 trillion stars. It is close as galaxies go, and the word close has to carry an absurd load. At Voyager speed, the crossing from here to Andromeda would take on the order of 40 billion years, roughly 3 times the current age of the universe. If we sent a signal today, and some listener there replied instantly, the answer would arrive 5 million years from now, to whatever Earth has become. Intergalactic space is not a bigger version of interplanetary space. It is a different category of separation, and Andromeda is the mildest possible example, the first stepping stone, unreachable by a margin of 40 billion years. But Andromeda earned its place on this list with a twist no other entry has. It is the one unreachable place that has been coming to us. Measurements dating back to 1912 show Andromeda's light shifted toward the blue, meaning the galaxy approaches, currently at about 110 kilometers per second. For a century, textbooks carried the consequence. In about 4.5 billion years, the Milky Way and Andromeda would collide and merge over billions of years into a single giant elliptical galaxy, which writers took to calling Milkomeda. The meeting was one of the firmest appointments in cosmic forecasting. The destination we could never reach was scheduled to reach us. Then, in June 2025, the appointment honestly dissolved. A study led by Till Sawala, published in Nature Astronomy, revisited the problem with updated measurements from the Gaia and Hubble telescopes and ran 100,000 simulations of the local group's future, this time fully accounting for the gravitational influence of the other members of the neighborhood, especially the Triangulum Galaxy and the Large Magellanic Cloud. The Large Magellanic Cloud, it turns out, tugs the Milky Way sideways, perpendicular to the line toward Andromeda, and that small sideways pull compounds over billions of years. The result made headlines among astronomers. The probability of a Milky Way and Andromeda merger within the next 10 billion years came out near 50%, a coin flip, and the classic head-on collision in 4.5 billion years dropped to only about a 2% likelihood. The most famous collision in astronomy is now officially uncertain, pending better data on the sideways drift of two galaxies. Two details deserve to travel with that revision. First, even if the merger happens, it is not a collision in any everyday sense. Stars are so small compared to the space between them that when galaxies merge, essentially no two stars ever strike each other. The galaxies pass through one another like two clouds of gnats, are bent by gravity, fall back, pass through again, and settle, over billions of years, into a single swarm. Second, whatever the outcome, no human institution is invited. The earliest possible encounter lies 1,000 times deeper in the future than our species is old. Andromeda may come to us, and the meeting still would not include anyone. So the entry stands with a gentle irony attached. The one destination on tonight's list that might do the traveling on our behalf may now decline the trip, and if it accepts, it arrives on a schedule that has nothing to do with anybody. The visit may happen. The meeting never will. In the meantime, Andromeda remains what it has always been for our species, the farthest place a naked human eye can touch, with sight and with nothing else. The measurement of Andromeda's distance is one of the hinge moments of modern thought, and it deserves its scene. As late as 1920, astronomy's leaders formally debated whether the spiral clouds in the sky were small nearby objects inside the Milky Way, or entire distant galaxies of their own, and the question was considered possibly unanswerable. In October 1923, Edwin Hubble, working at the 100-inch telescope on Mount Wilson, photographed a plate of Andromeda and marked a star he first took for a nova, crossing it out and writing VAR with an exclamation mark when he realized it was a Cepheid variable, a type of star whose pulsation period reveals its true brightness and therefore its distance. The little star's arithmetic placed Andromeda far beyond any possible edge of the Milky Way. That single plate multiplied the size of the known universe by an enormous factor and demoted our galaxy from being the universe to being one of its citizens. The smudge in the autumn sky is the object that taught our species how big everything is, which gives it a strange double role tonight, the first proof of other galaxies and the nearest example of how unreachable they all are. The approach itself was spotted even earlier, and it was a surprise of the opposite kind. In 1912, at Lowell Observatory in Arizona, Vesto Slipher measured the spectrum of Andromeda and found its light shifted toward the blue, indicating approach at hundreds of kilometers per second. Within a decade, he and others found that nearly every other galaxy showed the opposite. Light shifted red, receding, the raw data of what became the expanding universe. Andromeda is the great exception, one of the very few large blue-shifted objects in the sky, close enough that its gravitational tie to the Milky Way overpowers the general expansion. In a universe where essentially everything is leaving, our nearest peer is inbound, which is precisely why the question of the collision was taken seriously for a century, and why its recent demotion to a coin flip counts as genuine news about our galaxy's biography. If the merger does come, the show from inside would be slower and stranger than the word collision suggests. Simulations paint the sequence. Andromeda swells over billions of years from a smudge to a broad glowing band. The two galaxies sweep past each other, tearing luminous streamers of stars across the sky, then fall back and interpenetrate, their gas clouds igniting fireworks of new star formation, while the night skies of any surviving worlds fill with structures no current sky contains. Stars themselves will almost never collide, but many will be flung onto new orbits, and our Sun, if it still shines, could be thrown to the merged galaxy's outskirts or dropped toward its core. Eventually, the two spiral disks dissolve into a single, featureless swarm of ancient stars. Every step of that story, whichever version of it runs, will happen without a single decision by anything descended from us mattering to the outcome. It is the rarest kind of event this list contains, an arrival we can only await, and now, honestly, not even predict. Seeing it for yourself is worth the small effort, and the experience rearranges something. On a moonless autumn evening, away from city glow, find the great square of Pegasus, step along the chain of Andromeda's stars, and look for a faint elongated softness, like a thumbprint on the sky's glass. Averted vision helps, glancing slightly aside so the eye's more sensitive periphery does the work. That soft smudge is 1 trillion suns, compressed by distance into something dimmer than a candle across a valley. And consider what physically happens in the moment of seeing. Photons that left Andromeda's stars 2.5 million years ago, when our ancestors were small and few in East Africa, cross the last few centimeters of Earth's air, pass through the lens of your eye, and end their existence against your retina, triggering the signal you experience as a faint gray glow. Intergalactic light, terminated by contact with a living nervous system. It is the only physical connection to another galaxy any human being will ever have, and it is real contact, matter to light to matter, across a gulf of 25 billion kilometers. Sight, the consolation running through this entire list, is at its least consoling and most miraculous here, where the naked eye personally receives the farthest mail it will ever be sent. Andromeda also keeps its own version of everything this list has counted. It has a supermassive black hole at its center, over 100 million solar masses, dozens of times heavier than ours, a forbidden interior to rival our entry at number 9. It has its own halo of satellite galaxies, its own star-forming nebulae with their own pillars, its own dead stars with untouchable surfaces, presumably its own Oort clouds trailing its own 1 trillion stars, and, if anything thinks there, its own version of tonight's countdown, in which a barred spiral galaxy, 2.5 million light-years away, ours, hangs in their sky as the farthest thing their unaided observers can see. Every entry on our list has a mirror in theirs. Unreachability, whatever else it is, appears to be evenly distributed, and the two galaxies face each other across the gap like two shores that will never exchange a boat, each visible from the other, each certain the other is real, each permanently uncrossed. And whether or not Andromeda ever arrives, there is a deeper current beneath the question, because both galaxies, ours and theirs, are already falling together towards something much larger, a destination in the southern sky that neither will ever reach. It is the next entry on the list. Number 7, the Great Attractor. In the mid-1980s, a group of 7 astronomers, who came to be known in the field as the 7 Samurai, set out to measure how galaxies in our corner of the universe are moving. They expected the tidy outward flow of cosmic expansion, every galaxy receding from every other. What they found instead was a current. The Milky Way, Andromeda, and thousands of neighboring galaxies are all streaming in the same direction, toward a point in the southern sky, at roughly 600 kilometers per second. Something out there, 150 to 250 million light-years away, is pulling the entire neighborhood toward itself. Lacking a better name, the astronomers called it the Great Attractor, and the name has held for 40 years, in part because we have still never properly seen it. The reason we cannot see it is almost comically unfair. The Great Attractor happens to lie behind the plane of our own galaxy, in the region astronomers call the Zone of Avoidance, where the Milky Way's dust and crowded star fields blot out roughly a fifth of the extragalactic sky at visible wavelengths. The largest gravitational landmark in our cosmic neighborhood sits directly behind the one curtain we cannot pull aside. To study it at all, astronomers have gone around the curtain, using X-rays and radio waves that pierce the dust. In 1996, those methods found a huge concentration of galaxies, the Norma cluster, sitting near the attractor's expected position. But the tallied mass came up short of what the flow demands, and the modern picture is layered. Part of the pull comes from the Norma region. Part traces much farther back to the enormous Shapley supercluster behind it, more than 600 million light-years away. And in 2017, mapping of the local flows revealed that part of our motion is not a pull at all, but a push from an enormous empty region on the opposite side of the sky that came to be called the dipole repeller. We are squeezed between an absence behind us and an abundance ahead. The full frame arrived in 2014, when the cosmographer Brent Tully and his colleagues mapped the flows of 100,000 galaxies and drew a boundary around all the currents that drain toward our attractor basin. They named the enclosed region Laniakea, a Hawaiian word meaning immense heaven, a supercluster 500 million light-years across, with the Milky Way drifting near one edge. Every galaxy inside Laniakea is falling, in the long, slow sense, toward the same drain, and the drain is the Great Attractor. Since the day you were born, you have traveled roughly the distance from the Earth to the Sun toward it, without feeling a thing. The scale of that motion bears repeating. 600 kilometers per second is more than 2 million kilometers per hour, and it is the speed of your standing still. And now the sentence that earns this entry its rank on a list of places we can never reach. We are falling toward the Great Attractor, and we will never arrive. The same dark energy that will dominate the final entries of this countdown is accelerating the expansion of space, and on Laniakea's scale, expansion wins. The supercluster is not gravitationally bound. Its parts, our galaxy included, will ultimately be carried away from one another faster than they fall together. The current we ride is real, the destination is real, and the arithmetic of the universe has already ruled that the two never meet. The Great Attractor is the strangest kind of unreachable place, one we are actively traveling toward at 2 million kilometers per hour, on a road that stretches faster than anything can drive. The people who found this thing deserve their moment, because the discovery was an accident of ambition. In the mid-1980s, 7 astronomers, among them Sandra Faber, Alan Dressler, and David Burstein, set out to survey elliptical galaxies and refine the cosmic distance scale, a respectable, unglamorous goal. Colleagues nicknamed them the 7 Samurai. Their data kept insisting on something they had not looked for, a coherent streaming of galaxies across a colossal region of sky, everything drifting the same way, as if the local universe were water in a tilted basin. They announced the flow in 1986 and, needing a name for whatever lay downstream, coined the Great Attractor, a deliberately theatrical label for a mass they could not see. The finding was initially controversial, as enormous unlooked-for results tend to be, and it survived every challenge. It stands as a model of how science actually advances, a team measuring one thing carefully enough to discover a different thing entirely. It is worth being precise about what the 600 km per second figure means, because the bookkeeping is elegant. The universe's expansion carries every distant galaxy away from us in a smooth, predictable pattern, and astronomers can subtract that pattern from any galaxy's measured motion. What remains after the subtraction is called peculiar velocity, the galaxy's private motion. It's swimming against or across the current. Our local group's peculiar velocity is the 600 kilometers per second in question, and it is independently confirmed by the temperature pattern our motion prints on the cosmic microwave background, the same speedometer in the sky that measured the first entry of this countdown. The smallest item on tonight's list, and this one, are verified by the identical experiment, which is the kind of internal rhyme the universe occasionally allows. Mapping continues to fill in the basin we are sliding through. Surveys peering through the galactic dust with X-rays and radio waves have traced the Norma cluster's neighborhood in increasing detail, and in 2016, a team announced the Vela supercluster, another enormous mass concentration lurking partly behind the zone of avoidance, adding its pull to the ledger. The modern picture stacks attractors behind attractors, Norma, then Vela's contribution, then mighty Shapley at 650 million light-years, with the dipole repeller's emptiness pushing from behind, and our motion is the sum of the whole invoice. Some cosmologists suspect the full accounting still is not closed, that flows on even larger scales remain to be charted. We know our speed to within a few kilometers per second. What we still cannot fully list is everything we owe it to, which makes our destination not only unreachable but, in part, still unidentified. Dark energy decides that fall, and dark energy will return before this list ends. But the next two entries owe their no-entry signs to something older and stranger than expansion, doors built into the geometry of space itself, and the first of them is the largest door of its kind ever measured. Number 6. The Event Horizon of TON 618. In 1957, a survey of faint blue objects conducted from the Tonantzintlo Observatory in Mexico catalogued an anonymous dot of light and labeled it Entry 618. Nobody paid it special attention. The word quasar had not yet been coined, and no one imagined that some faint blue dots were the burning hearts of distant galaxies. Only years later did the spectrum of TON 618 reveal what it actually is, a quasar roughly 10 billion light-years away, shining with the light of perhaps 100 Milky Ways, powered by one of the most massive black holes ever measured. The mass measurement comes from the gas. Around the central object, clouds orbit at thousands of kilometers per second, and the speed of that orbiting gas, read from the width of the object's spectral lines, weighs the thing it circles. The answer for TON 618 comes out near 66 billion times the mass of the Sun. 66 billion. The entire Milky Way's black hole, the Sagittarius A star we visited 3 entries ago, holds about 4 million solar masses, and it dominates the orbits of stars across light-years. TON 618's central mass outweighs it 16,000 times over. Some candidates may go higher still. An object known as Phoenix A has been estimated near 100 billion solar masses, though that figure carries honest uncertainty. Somewhere in this class sits the heaviest single object in the universe. Mass on that scale reshapes the geometry around it, and the numbers describing TON 618's event horizon, the boundary of no return, are the kind you have to walk around slowly. The horizon's radius is roughly 195 billion kilometers, which is about 1,300 astronomical units. If TON 618 replaced the Sun, its event horizon would not merely swallow the planets. It would extend more than 40 times farther out than Pluto's orbit. The whole architecture of our solar system, planets, Kuiper belt and all, would fit inside this one black hole's boundary hundreds of times over. Light itself, the fastest traveler there is, would need days to cross from one side of the horizon to the other. There are single objects in this universe wider than the entire map most of us grew up memorizing. As a destination, the horizon of TON 618 is sealed twice, and the two seals are of entirely different kinds. The first is the familiar one, distance. 10 billion light-years puts it 3/4 of the way across observable cosmic history. The light we receive from it left before the Earth existed, when the universe was less than 1/3 of its current age. Every travel time figure this list has quoted so far becomes silly at this range, so we can let the arithmetic rest. The second seal is the interesting one, because it does not depend on distance at all. An event horizon is not a surface in the ordinary sense, not rock, not gas, not anything material. It is a boundary in space-time itself, defined by a single property. From inside it, no path leads out. Not for rockets, not for signals, not for light. A spacecraft could, in principle, park safely outside it and watch, the way the Event Horizon Telescope watched the horizons of other black holes from Earth. But the boundary itself marks the line where visiting becomes vanishing. The horizon of TON 618 is a door 1,300 astronomical units wide that only opens inward, and the universe manufactures such doors in every size, from city-sized stellar horizons to this, the largest measured door there is. The word quasar itself records how badly these objects once broke astronomy. Through the 1950s, radio surveys kept finding powerful sources that matched, in photographs, nothing but faint star-like points, and the community filed them as quasi-stellar radio sources, a name that means we do not know what these are. The break came in 1963, when Martin Schmidt at Caltech stared at the gibberish spectrum of the object 3C273 and realized the lines were perfectly ordinary hydrogen, shifted redward by an amount that placed the object billions of light-years away, which meant its intrinsic brightness was hundreds of times an entire galaxy's. The only engine anyone could make work on paper was gravity, matter spiraling into a compact supermassive object, heating white-hot as it fell. Quasars were the first evidence that giant black holes exist, decades before any horizon was photographed, and TON 618 is simply the case where the engine's scale still stuns even the specialists who spend careers on such objects. The physics of that shine is worth one calm paragraph. A black hole emits nothing, but matter falling toward one forms a whirlpool, an accretion disk, where friction and compression heat the gas to hundreds of thousands of degrees, making the disk glow across the spectrum before the material crosses the horizon. This process converts mass to light with an efficiency roughly 10 times that of nuclear fusion, which is why a single feeding black hole can outshine the 100 billion fusion reactors of its host galaxy. TON 618's output, around 100 trillion times the Sun's, represents a feeding rate of whole solar masses of gas consumed in short order, sustained long enough to build a 66 billion Sun account. And such growth may carry a natural ceiling. Theorists calculate that much above roughly 100 billion solar masses, an accretion disk begins to disrupt its own supply. So objects in the TON 618 and Phoenix A class may sit near the largest mass any black hole in this universe can practically reach. This entry, in other words, may be within sight of a genuine cosmic maximum, the heaviest single thing's existence permits itself. Two quiet numbers complete the picture, and both invert expectations. First, density. Because a horizon's radius grows in direct proportion to mass, the volume grows much faster, and the average density inside an ultramassive horizon falls to almost nothing. Spread TON 618's mass through its horizon's volume, and the result is thinner than the air in this room. Crossing such a horizon would involve no crash into anything dense, only a soundless passage through a mathematical line in vacuum. Second, time. To a distant observer, clocks near a horizon run slow, and light climbing away arrives stretched and dimmed, so a probe descending toward that boundary would appear to slow, redden, and fade without ever quite seeming to cross, its last image preserved like an insect in amber, while its own experience carried it onward and inward. The largest doors in the universe are not merely one way. Seen from outside, they never even finish closing on what they take. A door that size can be seen shining across 10 billion light-years, which raises a natural question. What is the farthest thing anything has ever seen? The answer holds the next spot on our countdown, and with it, the list crosses a line. Every entry so far has been unreachable in practice. The next one is unreachable in principle. Number 5. MZ14, the most distant place ever seen. The current record holder for the most distant confirmed object in the universe is a small galaxy with an unglamorous catalogue name, MZ14. The James Webb Space Telescope confirmed it spectroscopically at a redshift of 14.44, which translates into a statement that takes a moment to accept. The light Webb collected from this galaxy left it about 280 million years after the Big Bang. The universe was 2% of its current age. Nothing older has ever been confirmed by direct measurement of its light. Webb took the record from the previous holder, a galaxy called Jade's GZ14, announced in May 24, and the pattern in these record breakers is itself a scientific puzzle. The earliest galaxies keep turning out startlingly luminous, far brighter than pre-Webb theory predicted for such young cosmic times, as if the universe learned to build galaxies faster than our models allow. That puzzle, the too bright dawn, is one of the liveliest open questions in astronomy. But tonight's interest in MZ14 is not its brightness. It is what the word distance does when you push it this far, because at this range, distance itself splits in two. The first number is the light travel distance. The photons Webb caught spent about 13.5 billion years in flight. That number is honest but incomplete, because during those 13.5 billion years, the universe kept expanding, carrying the galaxy farther away while its old light was still en route. Ask instead where MZ14, or whatever it has become, is located now, and the answer is the second number, roughly 33 to 34 billion light-years away. The place whose baby picture we just took has moved to an address more than twice as far as the light's journey suggests. And now the decisive fact, the one that changes the character of this entire list. Because of the expansion of space, MZ14 is receding from us faster than the speed of light. No law of physics is violated by that sentence. Relativity forbids anything from moving through space faster than light, and nothing does. But space itself is free to stretch, and it stretches everywhere at once. So the more space lies between 2 points, the faster the total gap grows. Beyond a certain distance, the stretching between here and there adds up faster than light can cross it. MZ14 sits far beyond that line. Consider what that means for reachability, stated plainly. Launch a probe tonight at 99.99% of the speed of light. Give it infinite fuel, a perfect hull, and eternity to fly. It never arrives. Not in a trillion years, not ever. The distance between the probe and the destination grows faster than the probe can eat it, like a runner on a track that lengthens 2 meters for every meter run. Every entry on this list so far, the Sun's core, Planet 9, the galactic center, even Andromeda, has been unreachable the way a mountain is unclimbable, by practical impossibility. MZ14 is unreachable the way yesterday is unreachable. The geometry of the universe has already closed the route in both directions. No probe of ours can ever touch it, and no signal we send, at any power, in any era, will ever arrive. We have photographed a place to which not even a message of hello can ever be delivered. The record will fall, as records do. Webb or its successors will confirm something at redshift 15 or 16, and the specific name in this entry will be updated. The lesson will not change. The farthest places we can see are places the universe has permanently disconnected from us, and we see them anyway, which may be the strangest privilege on tonight's list. The tool that makes such measurements possible deserves a gentle unpacking, because redshift is the ruler for everything this far out. As space expands, light traveling through it is stretched with it, its wavelength lengthening, its color shifting redward. Astronomers express the stretch as a number, and MOMZ14's redshift of 14.44 means every wave of its light arrives more than 15 times longer than it left. Ultraviolet light from its newborn stars, the harshest glare a young galaxy makes, reaches Webb as tame infrared warmth. That is why this discovery required Webb at all. The most energetic light of the early universe arrives at Earth as heat, and only a telescope chilled behind a tennis court sunshield, parked beyond the moon, watching in the infrared, can read it. The record was then certified by spectroscopy, the splitting of the galaxy's faint glow into a rainbow bearing a sharp cliff-edge feature, the Lyman break, whose exact position nails the redshift beyond argument. Photometric guesses can flatter and deceive. A spectrum is a signed confession. What Webb has found at these depths, at MOMZ14 and its rivals, amounts to a pleasant crisis. The galaxy is small by today's standards, but startlingly bright, and it contains the chemical fingerprints of elements forged by earlier generations of stars, at a cosmic moment when, by the old models, there had scarcely been time for stars to form, die, and seed the gas at all. It is not alone. Webb's longest stares at the dark are crowded with early galaxies more luminous, more numerous, and more mature than pre-launch theory expected. And the explanations in play, star formation in intense bursts, unusually efficient conversion of gas into stars, early feeding black holes adding their light, are being argued through the journals right now. Nobody believes the Big Bang framework is in danger. What is in revision is the tempo of the universe's first act, which appears to have opened faster and louder than anyone scored it. The most distant place ever seen is also, currently, a place our theories are running to catch up with. There is one more temporal fold worth taking to bed, because it is this entry's quietest strangeness. MOMZ14, as photographed, is a newborn, 280 million years old, in a universe now approaching 14 billion. Whatever it truly is tonight, a grown spiral, a swallowed satellite inside some giant elliptical, a name no one will ever attach, it has had over 13 billion years of history since the light we possess left it, and none of that history can ever be reported to us. The expansion that carried it beyond reach also guarantees the news can never be updated. Its later light will arrive ever more slowly, ever more stretched, a book whose remaining pages turn more and more slowly forever, without ending. We do not just see this galaxy as it was. We see the only version of it we will ever be permitted, an infancy preserved in transit, sent from an address that no longer means anything, by a sender that no longer exists in any form we could confirm. A place no signal can ever touch seems like it should be the extreme case of unreachability. It is not. The strangest entry on this list is stranger, because it is a place a traveler genuinely could enter, tonight, with nothing but a rocket and patience. The entering is easy. It is everything afterward that the universe forbids. Number 4. The interior of a black hole. Every place on this list shares one property. We cannot reach it. This entry is the exception that proves how strange the rule can get, because the interior of a black hole is reachable. It may be the easiest destination in this entire countdown. Point a spacecraft at one, fall, and physics does the rest. The reason it belongs here, ranked above almost everything else, is a technicality with the weight of a tombstone. The traveler who reaches it can never, in any way, by any channel, tell anyone. Arrival and disappearance are the same event. It is a place we can never reach, because the we who reached it would no longer belong to the universe that sent them. The physics deserves to be told carefully, because the folklore gets it wrong in both directions. Start with the crossing itself. An event horizon is not a wall, not a surface, not a barrier you could touch. For a large black hole, a supermassive one like the giant in the galaxy M87, whose horizon was photographed by the Event Horizon Telescope in April 2019, the crossing would be locally uneventful. A falling traveler would notice no jolt, no flash, no sign at the threshold. The tidal forces at a supermassive horizon are gentler than the ones you feel standing on Earth. You could cross the most absolute boundary in physics mid-sentence and finish the sentence. Small black holes are less polite. For a stellar mass object like Cygnus X1, about 21 times the Sun's mass, the gravity gradient near the horizon is savage. The pull on a traveler's feet would exceed the pull on their head by so much that any object or person would be stretched into a thin stream of matter, a fate physicists genuinely call spaghettification. This is not theory alone. In 2020, astronomers watched a star wander too close to a distant black hole and observed the event called AT2019 QIZ. A star pulled into threads and partly swallowed. Its shredding lit up for telescopes across 500 million light-years. The universe demonstrates the mechanism on stars, so we are spared the need to demonstrate it on probes. So let the destination be a supermassive interior, and let us go, in the only way we can, in imagination and in the present tense. The crossing comes and goes without ceremony. Behind, the outside universe does not vanish. It condenses, gathering itself into a shrinking, brightening disk of sky framed in darkness, every star you have ever known collected into one jeweled window. Ahead, there is nothing to see, and the nothing is not empty. It is the future. Inside the horizon, the roles of space and time have quietly exchanged duties. The center of the black hole is no longer a location in any direction you could point to. It is a moment, an event waiting downstream, as unavoidable as tomorrow morning. Firing engines does not help, and this is the detail that rearranges the mind. Thrust in any direction changes nothing about whether you meet the center. Every path through the interior, powered or coasting, brave or careful, ends there in finite time. For a supermassive interior, that time is generous by the standards of last words, minutes to hours of experienced, thinking, watching existence. The interior is not a place where you are destroyed at the door. It is a place where the future has been narrowed to a single appointment. What actually waits at the appointment is one of the deepest open questions in science. General relativity, taken at its word, predicts a singularity, a point where density and curvature run to infinity and the equations stop meaning anything. Roger Penrose proved in 1965 that such breakdowns are not rare accidents of symmetry, but generic outcomes of collapse, a theorem that earned him the Nobel Prize in Physics in 2020. But almost no physicist believes the infinity itself. An infinity in an equation is usually the mathematics raising its hand to say, something deeper takes over here. The candidates for that something carry wonderful names: Planck stars, fuzzballs, smooth quantum cores, and none has been tested because the only laboratory that could settle the question destroys its own findings. Stephen Hawking added the sharpest twist in 1974, showing that black holes are not quite eternal, that they leak a faint quantum glow and evaporate over unimaginable spans of time, which opened a puzzle about whether the information that falls in is truly lost. That argument, the information paradox, is still being fought in the journals half a century later. Notice, finally, the perfect inversion this entry performs on the rest of tonight's list. Every other place is a place we can see and never touch. The black hole interior is a place we can touch and never see, from outside, even in principle. Whatever is learned in there stays in there. It is the universe's only sealed room with an always open door, and the door works in one direction, and the room keeps its counsel forever. The outside view of an infalling traveler completes this entry's strangeness, because the two accounts of the same journey refuse to match, and both are correct. Ride with the traveler, and the story is simple: a smooth fall, a crossing without incident, a finite interior, an ending. Stand back and watch, and relativity tells a different tale entirely. As the traveler nears the horizon, their signals climb out of an ever deeper gravitational well, arriving more and more slowly, stretched to lower frequencies, dimmer and redder, and their apparent motion decelerates without limit. From outside, the traveler never quite reaches the horizon. Their image slows, freezes, fades from red to black, and hangs there, an ember cooling into invisibility, while their own experience, in their own frame, carried them across and inward long ago. Physics in the middle of the 20th century actually called these objects frozen stars for this reason, before the modern name replaced it. The interior is thus doubly sealed. The traveler cannot send word out, and the universe outside cannot even watch them finish going in. It is worth being honest about where the gentleness ends, even for the supermassive case. The interior is survivable at the crossing, but it is not survivable indefinitely, because the same tidal stretching that shreds visitors at a small black hole's doorstep merely waits deeper inside a large one. As the falling traveler approaches the center, the difference in pull between head and foot grows without bound, and every extended object, given time, is drawn into the same thin thread. The interior of a supermassive black hole offers its guest an hour of wonders, a compressed and brightening view of the outside cosmos, geometry doing things no simulation fully renders, and then it forecloses. No account of those wonders has ever been written, and none ever will be. Every physics textbook description of the interior, including this one, is a calculation, not a report, and that distinction is the entire meaning of this entry. One genuinely open door of thought deserves mention before we leave, because black holes may concern more than travelers. Some serious cosmologists have explored whether the interior of a black hole could, under quantum gravity, bounce rather than terminate, budding off a new expanding region of space-time, and a few have gone as far as asking whether our own universe's beginning might admit such a description, an idea that remains speculation, clearly labeled, at the far edge of testability. Whatever the truth, the black hole interior is the one place in nature where our two great theories, general relativity and quantum mechanics, are both indispensable and mutually contradictory, which is why physicists want its secrets so badly. The most closed room in the universe is also the room most likely to contain the answer to physics' deepest question, and the rent for reading it is the one payment no scientist can make twice. For all its menace in this entry, the black hole deserves one correction on behalf of calm, because popular imagination gets the danger backward. Black holes do not suck. Outside the horizon, a black hole's gravity is simply gravity, identical to that of any other object of the same mass. If the Sun were replaced tonight by a black hole of exactly one solar mass, the Earth would not be drawn in by a millimeter. The planets would keep their orbits precisely. The tides would follow the Moon as always, and the only changes would be darkness and cold. Stars orbit our galaxy's central black hole for millions of years without incident, as we watched at Entry 9. The danger of a black hole is entirely a matter of trespass, confined to the region near and beyond the horizon, and the universe posts the boundary with perfect clarity. In a countdown full of places that cannot be reached, this is the one place that is only dangerous if reached, which makes it, for every practical purpose, among the safest objects in the sky to share a galaxy with. They are also nearer and more numerous than most people suspect, in a way that stays comfortably abstract. Our galaxy is estimated to contain on the order of 100 million stellar mass black holes, the quiet remnants of its most massive stars, almost all of them unlit, unfed, and undetectable. The nearest one currently known, found by the Gaia mission's star tracking, sits about 1,560 light-years away, orbited placidly by a sun-like companion star. Statistically, closer ones almost certainly exist, drifting dark through the disk. Each one is a sealed interior, a complete instance of tonight's entry, carrying whatever its collapse and its history delivered inward, holding it in a room the size of a city behind a door the size of physics. The strangest destination in the countdown is not rare. The galaxy is furnished with millions of copies, and every copy keeps its interior with the same absolute discretion. From the place that erases its arrivals, the countdown now turns to the oldest light in existence, and to the place it came from, a wall that stands behind every star in every sky. Number 3. The surface of last scattering, where the first light comes from. Point any sufficiently sensitive radio antenna at any patch of sky, and beneath the stars, beneath the galaxies, beneath everything, you will find a faint microwave glow that has no direction and no source you can step around. It is everywhere, arriving from every point of the sky at once, at a temperature of 2.7 degrees above absolute zero. It is the oldest light in the universe, the cosmic microwave background, and the place it comes from is the third entry on our list. The story of its discovery is one of science's best accidents. In 1964 and 65, two radio engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were commissioning a sensitive horn antenna and could not get rid of a persistent hiss. It came from every direction equally, day and night, season after season. They checked the wiring. They evicted a pair of pigeons roosting in the horn and scrubbed away what they politely recorded as white dielectric material. The hiss remained. It was the afterglow of the Big Bang, predicted years earlier and never found, and it earned Penzias and Wilson the Nobel Prize in 1978. Satellites have since turned that hiss into the most precisely measured signal in cosmology. The COBE mission in 1992, then WMAP, then Planck, mapped its temperature across the whole sky and found ripples of 1 part in 100,000, tiny warm and cool patches that are the seeds of every galaxy cluster now in existence, our own included. The baby picture of the universe hangs in every direction, and we have read its birthmarks. Now for the place itself. For its first 380,000 years, the universe was a glowing fog, a plasma so hot and dense that light could not travel freely. Every photon was scattered by free electrons within a fraction of a second of being emitted, the way light is scattered inside a cloud. Then the universe, expanding and cooling, dropped below about 3,000 Kelvin. Electrons and nuclei combined into neutral atoms, the fog cleared everywhere at once, and every photon in the cosmos was set free in a single cosmic moment. The light released in that single clearing moment is the light Penzias and Wilson caught in New Jersey, stretched by expansion from orange glow to microwave whisper. The shell of space from which our particular share of that light was released is called the surface of last scattering. It is not a wall or an object. It is a location, a set of regions that genuinely existed, made of ordinary matter, and those regions still exist in evolved form. Expansion has since carried them to a present-day distance of roughly 45 billion light-years. Their matter long ago condensed into stars and galaxies, And if observers live there now, they see our matter, as it was 13.8 billion years ago, glowing in their sky as their cosmic background. The wall we see is somebody's home, and our home is somebody's wall. Ride one of those photons, briefly, in the present tense. The fog thins, and for the first time in the history of anything, there is transparency, a longest possible line of sight snapping into existence in every direction. The flight begins. For millions of years, the journey is through darkness with no stars, the era before the first suns ignite. Then, slowly, structure kindles, the first stars, the first galaxies, and the photon threads between them, riding through a universe that keeps stretching its wavelength like taffy, orange to red to infrared to microwave. 13.8 billion years into the flight, a spiral galaxy drifts ahead, then a yellow star, then a small blue world, and the journey that began before the stars existed ends tonight, absorbed in a radio antenna, or in the static between stations, or in an eye on Earth. The light can make the trip. We cannot. That phrase was planted at the sun's core, near the start of this list, for sunlight 100,000 years old. It was always meant to arrive here, where the age of the light is the age of the universe. The surface of last scattering is unreachable in a way that outdoes even the previous entry, because it recedes by definition. Travel toward it, at any speed for any duration, and you gain nothing, because tomorrow's cosmic background arrives from slightly farther away, released fog light that has taken slightly longer to reach wherever you now are. It is a horizon made of light, the inside surface of the visible universe, and like the horizon at sea, it moves when you move. It also marks the hard edge of sight itself. Beyond it, meaning earlier than it, the universe was opaque, and no telescope at any size, in any era, will ever image anything from before the clearing by light alone. Only neutrinos and gravitational waves carry earlier news, and reading them at that depth remains beyond us. The most distant thing we can see is, by construction, a place that can never be stood in. It is everywhere, 45 billion light-years away, in every direction at once, and it is made of the same first morning. A homelier detail belongs in this entry, because the first light is not confined to observatories. The cosmic microwave background is bright by radio standards, and it leaks into ordinary life. In the era of analog television, a set tuned between stations displayed a screen of hissing static, and roughly 1% of that dancing snow was the cosmic microwave background itself, the Big Bang's afterglow, intercepted by a living room antenna and rendered as flicker. Anyone who ever watched static has watched light older than the stars. The same signal contributes a faint share of the hiss in any untuned radio. The most ancient thing perceivable was, for decades, a nightly nuisance in every household on Earth, which may be the single best example of how casually the universe distributes its treasures. The moment of release also repays imagination, because it looked like something. At 3000 Kelvin, the universe's fog glowed with the color of candlelight, and the release of the background was the whole cosmos, everywhere at once, shining orange like the inside of an ember, then slowly dimming and reddening as expansion stretched the glow toward invisibility. For its first few million years after the clearing, the universe had no stars, only that fading amber twilight thinning toward black, the era astronomers call the Dark Ages. Every point in today's universe, including the space occupied by your bedroom, was once inside that glow. The first light is not a distant phenomenon we observe. It is a condition everything passed through, and its stretched remnant now washes through this room, through the walls, through you, about 400 photons in every cubic centimeter of space, everywhere, forever thinning. And the wall has a future, which ties this entry to the finale ahead. The background cools as the universe expands, its temperature falling in inverse proportion to the stretch. It was 3,000 degrees at release. It is 2.7 above absolute zero now, and in the far future, it will slide toward a whisper, indistinguishable from silence. Its wavelengths stretched to the size of galaxies, its photons diluted beyond any instrument's reach. The baby picture fades. Observers far enough downstream will inherit a universe that no longer displays its own birth certificate, and no effort of theirs will recover it. We happen to live while the first light is still legible, still arriving, still warm enough to measure to 6 decimal places. The oldest visible place will not remain visible forever, and that fact, more than any other, sets up the final 2 entries of tonight's list. That wall is where seeing ends. But reach ends far closer in, at a line drawn tonight through the middle of the visible sky, and everything beyond that line, including galaxies shining in tonight's telescopes, is already lost. That line is the next entry. Number 2, the cosmic event horizon, the line of no return in the sky. There is a distance, in every direction from where you are lying right now, beyond which the universe is already finished with us. It is called the cosmic event horizon, and it currently sits 16 to 18 billion light-years away. The definition is simple and merciless. Any galaxy beyond that line is being carried away by the expansion of space so quickly that nothing we send, ever, will arrive. Not a probe at the speed of light. Not a radio signal transmitted tonight and traveling forever. The signal would chase the galaxy eternally and eternally lose ground, because the space in between breeds new distance faster than light crosses the old distance. Inside the line, a light-speed message can, in principle, still win the race. Beyond the line, the race is over, and it was over before we knew there was a race. Be careful to keep this horizon separate from the edge of what we can see, because the two are wildly different, and the difference is the whole point. We can see out to about 45 billion light-years, the surface of last scattering from the previous entry, because ancient light from those regions was emitted long ago and has had the whole age of the universe to arrive. Seeing is a transaction with the past, and the past keeps delivering. Reaching is a transaction with the future, and the future is where expansion collects its toll. So sight extends nearly 3 times farther than reach ever will. The map of the visible universe is mostly a map of places that are, for every practical and impractical purpose, already gone. The reason the horizon exists at all is dark energy. In 1998, 2 rival teams measuring distant supernovae, expecting to clock how much the universe's expansion was slowing down, found instead that it is speeding up, a discovery that earned the Nobel Prize in 2011 and rewrote the ending of cosmology. Whatever drives the acceleration, and its nature remains the largest open question in physics, it makes up about 68% of the universe's energy budget. In a universe that decelerated, patience would eventually deliver any destination, however remote. In an accelerating universe, remote regions gain recession speed faster than any traveler gains ground, and so a permanent boundary of influence forms around every observer. The horizon is that boundary, our sphere of possible consequence, and it is shrinking, in the sense that galaxies keep leaving it. Estimates suggest that in every year that passes, tens of thousands of galaxies cross from the reachable side to the unreachable side. During the 3 hours of this video, the door will close on another handful of galaxies, each one home to hundreds of billions of stars, each one removed from every possible future itinerary, silently, without ceremony, while the list plays on. One honest asterisk belongs here. The horizon's exact future depends on dark energy holding steady, and recent measurements by the DESI survey have hinted at growing but not yet decisive confidence that dark energy's strength may be evolving over cosmic time. If that holds, The bookkeeping of the far future shifts, and cosmologists are watching closely. What does not shift is the present ledger. The line is real, its distance is measured, and everything beyond it is, for us, already over. The geometry underneath this line deserves one careful paragraph, because it contains a beautiful subtlety. There is a nearer distance, currently around 14 billion light-years, called the Hubble distance, where the expansion carries galaxies away at exactly the speed of light, and intuition insists that must be the wall. It is not, and the reason is lovely. A photon launched toward us from just beyond that line is initially losing ground, swept backward by expansion faster than it flies forward. But the photon keeps flying, and as the eons pass, it drifts into regions where the recession relative to us is slower, until it crosses into territory where it finally gains ground and completes the trip. Light can win from behind the light speed line, given enough time. The event horizon at 16 to 18 billion light-years is the deeper boundary, the line beyond which even that patient strategy fails forever, because acceleration keeps promoting the intervening space faster than the photon can demote it. The universe distinguishes between hard journeys and impossible ones, and it draws the two lines in different places. The horizon also has a personal version, and it is the entry's quietest fact. Because the cosmic event horizon is defined by what can eventually influence us, every year that passes moves more of the universe across it, and the accounting applies to signals we send as well as signals we might receive. A radio message broadcast from Earth tonight, traveling forever, will sweep across the reachable galaxies and then run out of universe it can touch, its frontier slowing against the stretch of space, asymptotically stalled. Everything humanity will ever say, at any power, in any language, has a maximum audience, fixed by geometry, and the maximum shrinks. There is a farthest star our species will ever influence, out there tonight, unmarked. No instrument can identify it, but the mathematics guarantees it exists, a last address on the longest possible mailing list, and every list after tonight's will be shorter. There is something quietly upending about the fact that the sky does not look like any of this. The galaxies beyond the horizon are not dim or fading or marked. Their old light arrives bright and detailed, fully present, while the galaxies themselves are permanently elsewhere. Which raises the last question of the countdown, the only one left. Once the line is drawn, how much of everything lies on the far side of it? That count is the number one entry on this list. Number 1, the unreachable universe. Almost everything, already gone. The number one place on tonight's list is not a single destination. It is the honest total, and here it is. Of the roughly 2 trillion galaxies estimated to populate the observable universe, about 94% are already beyond the cosmic event horizon's reach. Permanently. 94%. If humanity launched a probe tonight at the full speed of light and never stopped it, fewer than 1 galaxy in 10 could ever, under any circumstances, be its destination, and even those remaining few demand journeys of billions of years through space that is actively working against the trip. The reachable universe is a small bubble, and the bubble does not grow. It only loses. Say it the other way around, because the inversion is the thesis of the entire list. Unreachability is not the exception in this universe. It is the default condition of almost everything that exists. The 19 places counted down tonight were never oddities. They were samples, drawn from a cosmos that is, by measured majority, permanently elsewhere. Nearly everything there is belongs to the category this video is about, and the 94% is only the beginning of the count because it describes just the universe we can observe. The observable universe is a sphere about 93 billion light-years across, and it is centered on us, not because we are special, but because seeing is centered on the seer, Every observer anywhere sits at the middle of their own sphere of sight. What lies past the sphere is not nothing. It is more universe, regions whose light has never had time to reach Earth in all of cosmic history. How much more is a measured question with a humbling answer. The Planck satellite's final data, released in 2018, showed the universe's geometry to be flat to within a fraction of a percent, and that flatness implies the whole is at minimum hundreds of times larger in volume than the part we see. The theory of cosmic inflation suggests vastly more than that, and many cosmologists take seriously the possibility that it simply does not end at all. Every argument points the same direction. What we can see is a sample. What we can reach is a rounding error on the sample. Now let the clock run forward, because the finale of this list is not a place but a forecast. The acceleration continues. Galaxies now visible will, over the coming tens of billions of years, redshift beyond the reach of any instrument, their light stretched thinner and thinner until it slips below detection. Andromeda and the local group will have long since merged with us into one great elliptical swarm, the only gravitationally bound company the horizon leaves us. And on the order of 100 billion years from now, observers in that merged galaxy, if any exist, will look out with instruments as good as ours, or better, and find nothing. No other galaxies. No cosmic microwave background, stretched by then beyond any practical detection. No evidence that a Big Bang ever happened, no way to discover the expansion, no clue that their island of stars was once one of 2 trillion. They will conclude, from perfect observations honestly interpreted, that the universe is one galaxy floating in eternal black, and they will be wrong, with no possible way ever to learn it. The truth about the universe is a limited time offer, and the stock is being removed from the shelves at the speed of stretching space. The far future forecast has a name in the scientific literature, and the honesty of it is bracing. Cosmologists, notably Lawrence Krauss and Robert Scherer, in a paper published in 2007, worked through what observers in a galaxy like our merged future one would be able to deduce 100 billion years from now, and the answer is a kind of epistemic tragedy. With the background radiation stretched beyond detection and every unbound galaxy redshifted past visibility, the honest conclusion from all available evidence would be a static island universe floating in infinite empty space, precisely the cosmology humans believed a century ago, before Hubble's plate and Slipher's spectra corrected us. The expansion erases its own footprints. Knowledge we take for granted, that the universe is expanding, that it had a beginning, that there are trillions of galaxies, is only discoverable during a window of cosmic time, and the window closes. Astronomy is not a permanent inheritance. It is a harvest, and the season, cosmically speaking, is finite. Set against that forecast, the present acquires a texture it did not have 3 hours ago. Every telescope now operating is working the richest sky any observer in this universe's far future will ever be denied. The 2 trillion galaxies are all still, in the accountant's sense, on the books, visible if not visitable. The microwave background still hums in every direction at 2.7 degrees, legible to any species that builds a horn antenna and wonders about the hiss. The long stares still return galaxies whenever a mirror stares long enough at an empty-looking patch of dark. None of tonight's 20 entries, for all their locked doors, has ever refused us the one thing we actually asked of them, which was to be known. The universe has said no to every journey on this list, and yes, so far, to every question. Honesty requires displaying the other side of the ledger before the list closes, because the reachable crumbs are not crumbs. The 6% of the observable universe that remains within the cosmic event horizon still amounts to something like 100 billion galaxies, each with its hundreds of billions of stars, all of them, in the loosest and most generous sense, possible destinations for matter and signals from Earth. 100 billion galaxies is not a consolation prize by any standard except the one this entry sets. And far inside that allotment sits the portion that is truly, permanently ours, the gravitationally bound, local group, Andromeda, the Milky Way, and their several dozen attendant dwarf galaxies, the one neighborhood dark energy can never disassemble, a few trillion stars that will share a single merged sky for as long as stars can shine. The universe has subtracted almost everything, and what remains after the subtraction still exceeds what any species could exhaust in any span of time it is meaningful to write down. The 94% is a fact about the universe. The 6% is a fact about how much universe a fact can leave behind, and it is more than enough to be going on with. Which means something specific and strangely warm about tonight. We live inside the brief era, cosmically speaking, when the unreachable universe can at least be seen. The 2 trillion galaxies are still on display. The first light still arrives from 45 billion light-years away. The evidence of the beginning is still legible in every direction. Remember the very first entry of this countdown. The point in space where you started this video, a few hundred kilometers behind you. It has by now become millions of kilometers, and here at the end of the list, the smallest unreachable place and the largest turn out to obey the same rule. What recedes does not come back, and the receding is quiet, and the universe does not announce it. The galaxies crossing the horizon tonight leave exactly as your starting point left, without a sound, while everything appears, to every eye watching, entirely still. So the countdown ends with the ledger it promised. Almost everything that exists is already gone, in the only sense that ever concerns a traveler. And yet every one of those places remains, for now, something better than reachable. It remains visible. The one power that survives the whole list is the one you have been using for 3 hours, the power to look, to measure, to understand, from the one small place we do have. Sight was never the consolation prize. Across 94% of the universe, it is the entire relationship, and it is enough to have filled this night, and every night humanity has ever spent under the sky. And so the list closes where every journey on it ends, at home, under a ceiling of places that light alone will ever touch. The universe keeps its distances, and it keeps them gently, asking nothing of us but attention. Let the unreachable stay unreachable for tonight. It will all still be shining in the morning. Sleep well, and good night.